Hi, it's time for another math easy solution. Today we're going to go over further into the vectors and the geometry of space video series. And this time we're going to look at equations of lines and planes. Alright, so let's continue further. And note, as always, if you don't have time to watch this whole video, in this case, you can play this video at a faster speed. Yeah, there's no summary conclusions in this video. And also top secret life hack. As always, your brain gets used to faster speed. And here's a tutorial I made on it right here. And in this tutorial, I used this extension right here, mes.fm/video speed-extension. Anyways, going further, so you can also download and read the notes. If you don't have time to watch this whole video, you can also read the notes on the Hive blockchain. And you can also watch the video in parts, and all the timestamps of all the parts are in the description, as well as a link to all of these as well, these notes. And also, a new thing I've been doing is adding video sections playlist, and in this case, we'll have it available, and I'll upload, basically, this is going to be a long video, so I'm going to break it down into many sections, and then upload that as a playlist, and you can watch specific parts. Very interesting stuff. Now let's continue further. So calculus book reference. Note that I mainly follow along the following calculus book. This is Calculus Early Transcendental, 7th edition by James Stewart. And note, in the earlier videos, I used the 6th edition. Alright, continuing further. So sections in calculus book chapter. So I've made a list of the sections in this particular chapter with links to the Hive post of the videos that I've already finished. Note that I've started splitting each long video into sections and made a playlist for each. And here's a link to it. And again, the notes for this in PDF and Hive article format in the link description below. So this is vectors. I added the playlist here, vectors, and then the geometry of space. And then I added, so I made a video on 3D coordinate systems, and I have the link to the Hive post. And then we did vectors and so on. And then these playlists, these are indicates the section playlist, and that's a YouTube playlist right there. And continue further. So now the one we're doing currently is equations of lines and planes. Current video, and I also made a playlist on it. No videos are in there yet, but I'll upload the videos as I share this video, and then split this up and share these in the future. Yeah, which usually means pretty much a upload every 3 days after this one. Anyways, continue further. So cylinders, actually that's the next videos after this. Now let's continue further. So topics to cover, and now we're following to the video. Note that the timestamps will be included in the video description for each topic listed below. So in this video, we'll go over lines, vector, then we'll go over the vector equation of a line, then parametric equations of a line, then go over example 1, then solution to 1a, and solution to 1b, then direction numbers, symmetric equations of a line, example 2, and then look at solutions to 2a, solutions to 2b. Note on example 2, then we'll look at an equation of a line segment, then example 3, and then look at and look at planes, not lines. So now we're going to look at planes in this second part, and we're going to look at the vector equation of a plane, the scalar equation of a plane, and then example 4, then look at the linear equation of a plane, then example 5, example 6, parallel planes, right there, and then we're going to go over example 7 and solutions to them. Parts A and B of solution 7, and then look at note 1, 2 linear equations can represent a line, and note 2, line of intersection from 2 parametric planes, and then example 8, distance from a point to a plane, and then example 9, example 10, and exercise 1. Yes, fascinating stuff. Alright, so now let's jump right in and look at lines. So a line in the XY plane is determined when a point on the line and the direction of the line, its slope or angle of inclination, are given. So all you need is a point and then the angle. Then you have a line. The equation of a line can be written using the point-slope form, as we're used to. Just here actually, let's just draw this out. So the point-slope form is basically if you have a line like this, y minus y1 equals to m, the slope, x minus x1, like that. And then if you were to graph this out like this. This is x, this is the y, so then let's say you have a line, and the point on it is going to be the coordinates x1 and y1. And the slope right here is going to be our m. Like that. Alright, so that's in 2Ds, in 2 dimensions, or the xy plane. So now likewise, a line in 3-dimensional space is determined when we know a point, p naught, x naught, y naught, z naught, on L, and the direction of L. So if we have a line L in that, so all we need to know is a point and the direction of it. And that brings us to the vector equation of a plane. So in 3 dimensions, the direction of a line is conveniently described by a vector. So we let v be a vector parallel to L. Yeah, so then the vector, yeah, it could represent the direction of it, and then we just need a point on it. So let p, x, y, z be an arbitrary point on L, and let r, 0 vector, r not vector, and r vector be the position vectors of p naught and p. That is, they have representations. This is from the origin. This is OP naught and OP vectors. So that is, yeah, these are from the origin. So if the vector A is a vector with representation P naught P, as in the below figure, or as in the figure below, like writing it this way, then the triangle law for vector addition gives R vector equals R naught plus A. But since A and V, I'll draw this all out. A and V are parallel vectors. There's a scalar T such that such that A equals TV. So let's make sense of all of this. Yeah, so let's draw this out. Yeah, so let's say we had a point P, X, Y, Z to be an arbitrary point on a line. And again, we're doing in 3D right now. So let's say we had like this. All right, yeah, so this is the Z axis. Draw this a bit neater. And this is the Y axis. And this is the X axis like this. So we get a bit more 3D looking. Okay, so that's the X axis. So let's say we had a line, L. So this is our L. And let's say there's a point on this, and this is our P. So there's a point P on it, and this is, we'll call this P, X, Y, Z. Alright, so now we have X, Y, Z, and it's arbitrary point on L, and let R naught and R be the position vectors of P naught and P. Yes, and yeah, P naught is, so this is R naught and R, and we know that P naught is, again, it's just a line on L as well. So this is arbitrary point on L, and there's the other one, our starting point. Let's say we had a point right here, and we'll call this over here P naught, and this is going to be X naught, Y naught, Z naught, like that. And then the direction vectors are, and this is the origin, so let's draw the origin. Oh, so the representations are OP naught, that's going to be our R naught vector. So in other words, it goes from this origin all the way to here. This is going to be R naught, right, just like that. So that's R naught. And then this one here is going to be our R. So this is going to be our R vector, like that. And this is from O to P, and this is from O to P naught. That's these right here. Now, if A is the vector with representation P naught P, yes, in other words, it goes from P naught to P, so that's going to be like this, like that. Yeah, but it's a bit hard to see also. I'll draw this in red. So this is, draw this a bit better. This right here is going to be our A. Alright, so this one here, I'll call this A vector. And that is from, with the vector A, with the representation P naught to P. And then the triangle law for vector addition gives R equals to, this is R plus A. Yeah, so R equals R naught plus A. That's again as the triangle law. So R naught plus A equals this R vector. And I'll just write this down here. R vector equals to R naught plus A, like this. And then we're also told here, so let V be a vector parallel to L. So in other words, V is a vector parallel to it. So let's draw this like, just starting anywhere here. So it's parallel to this. Parallel like that, and let's call it as, this is V. So that means if it's parallel to it, that means, well, it's going to be parallel, it's going to be just a scalar multiple of this A, right here. Yeah, here, just fix that up, I just made it like that. So it's a scalar multiple, so in other words, a scalar T such, times it by A, it's a scalar T such that A, this vector, is equal to a scalar multiplied by this V. So it could be double, it could be half the length, whatever it is, as long as it's, well, parallel. And it's just a scalar multiple, so hence it's parallel. So that means then, so we have this, and A equals 2 T scalar times V. So then we could put this all together. R naught equals to, R vector equals to R naught vector plus t times times a scalar t, scalar t times it by a parallel vector v to the line. All right, continuing further. So this above equation, so the above equation is called a vector equation of L. So each value of the parameter t gives the position vector r of a point on L. In other words, as t varies, as you change it, the line is traced out by the tip of the vector r. Yeah, so then as this vector here, this vector goes along this L line based on whatever the parameter t is. And in other words, as t varies, the line is traced out by the tip of the vector r. So as the figure below indicates, positive values of t correspond to points on L that lie on one side of p naught, whereas negative values of t correspond to points that lie on the other side of p naught. Again, depends. So, for example, here, let's graph this out. All right, so we have right here, so move it over like this. This is the z-axis, and move it up, and this is the y. This is the x, like that. So let's say we had our line L, and then we had, there's the origin, and then there's our point right here. Let's say this is the at t is equal to 0. Yes, if you go back to our vector equations, if t equals 0, r naught is just equal to r is just equal to r naught vector. So let's point this out. This is at our r naught like that, and this is at t is equal to 0. And then if t was, let's say, greater than 0, you're gonna have vectors like this. This would be the r. This would be the r, etc. And this is, again, that's our L. This is for t is greater than 0. Likewise, you'll have it going back like this if t is a scalar less than 0. So this is going to be like this, start like this. This is for t is less than 0. Yeah, so these values are all the vector equation. R, just put the r like that. And then, it becomes r, fluctuates based on the value of t, and if t is equal to 0, it just becomes r naught, the starting point. All right, let's go further and look at now parametric equations of a line. So if the vector v that gives the direction of the line L is written in component form as v equals the triangle bracket for vector components, a, b, c, then we have tv equals to ta, tb, tc. And again, remember the vector v is this direction right here parallel to the line. All right. We can also write r equals to x, y, z, and then r naught equals to the components x naught, y naught, z naught. So the earlier vector equation becomes, so this vector equation right here, and write these all in component form, it's going to be r naught equals to, let's write let's write the whole thing, t v vector like that, and then all in component form. This is the same as writing x, y, z is equal to, fix up the z, x, y, z equals to, this is x naught, the first starting point, y naught, and then z naught, like that. And then plus t, let's write this for completeness, plus, and then this is the t times v, where v is abc, and then t times v is going to be ta, tb, etc., tc. So ta, tb, tc, and those are the components, like that. And since they are components, we can just add these all up. So this is going to be, and I'll write this out so we can box this whole equation, x, y, z, like this, with these commas better, equals to, and then add these up, so vector addition, just x naught plus ta, etc. So x naught plus ta, and then this, not Then we put a comma. Yeah, the next one's going to be y naught plus tb, comma, then the z component, z naught plus tc, like that, and box this whole thing in. And actually, I'm just going to rearrange this because my calculus book rearranges it. It writes AT, BT, etc. Again, that's just copying my calculus book. And yeah, just flip it around like that. It doesn't change anything, but just the notation, just how it looks like. Alright, so that's written in vectors, but now two vectors, they are equal if and only if their corresponding components are equal. So therefore, if these two vectors are equal, each component is equal to it. So this x is going to equal to this y is equal to this, etc. And the z is equal to this right here, equals to this. So, therefore, we have the three scalar equations as opposed to writing in this vector component form. We can write these as scalars, so there's no vectors involved. Yeah, so x equals 2, well, it's just going to be this part. So x naught plus a t, and then the next one is y equals to y naught plus bt, and then the next one is z equals to z naught plus ct, like that. And let's just make this in the center. Move this over. So yeah, these are our three scalar equations. And the t value is defined for all real numbers. So t is an element of the set of all real numbers. It could be anything positive, negative, and so on, as long as it's a real number, not a complex that we've defined it for in this particular case. And now these equations are called parametric equations of the line L through the point P naught, X naught, Y naught, Z naught, and parallel to the vector V with components A, B, and C. Again, the parametric equations because they all have this parameter T there. And each value of the parameter T gives a point X, Y, Z, or X, Y, Z on the line L. It's very, very interesting. Alright, and now let's continue further and take a look at an example on this. So example 1, and this states find a vector equation and parametric equations for the line that passes through the point P1, 3, 5 and is parallel to the vector I plus 4j minus 2k. Yeah, and this is the written in standard basis vector form. And then part B says find two other points on the line. So solutions to 1a, we got to find the vector and parametric equations. So let's graph out what we are given firsthand. Yeah, just to grasp it. All right. So what we have is, let's just draw this z. It's like this, and then we have the y like this. And let's draw the z. The x is going to be something like this. That's our x. And now the points that we are asked to graph is 5, 1, 3. So we have 5. Let's go 1, 2, 3, 4, 5 is the first point. Then 1. It goes down like this one. And then it goes up 3. 1, 2, 3. So it should be somewhere around like here-ish. Let's say this is the point. This is the point right here. 5, 1, 3. That's the point. And it's going to have, well, the position vector R naught, like that. That's it aims over there, and it's parallel to the vector I. This is going to be I 4 and then negative 2. Yeah, so in other words, the V is going to be, well, 1. So if we start from here, it's going to be parallel to it. So let's go 1 xy's, and then we're going to go 4 on the y direction. We're going to go 1, 2, 3, 4, like that. So it should be somewhere above here. And then it's going to go minus 2. It's going to go in minus 2 direction. So let's say it goes like this. Let's go 1, 2, 3, 4, and then minus 2. 1, 2. So it's going to be going down. This vector like that, let's call this as our V vector. Over here, just erase that stuff there. So vectors like that's going to be pointing down, and this is going to be at our I. Plus 4j minus 2k. And that's parallel to it, so then it's going to be right on it. So we're drawing it right on it, like that, and there's that line L. like that. It's going downwards like that. All right, so that's what we have is, well, we got r naught is equal to, and write this in standard basis form just to make it all the same. Well, I'll write this first like this. In component form is going to be 5, 1, 3, and then this equals to 5i plus j plus 3k, like that. All right, we have that, and the next one is, we'll just write our regular parallel vector, v, this equals to, well, for completeness sake, let's write it in both forms. Write this as 1, 4, -2 in the components like that. This just equals to I plus 4j minus 2k, like that. All right, so the vector equation becomes r naught, just r, is going to be equal to, well, we got to write the vector equation. R naught, r vector plus r naught, equals to r naught plus t v, like that. And this just equals 2, and calculus book just wrote them in this format, so I'll write everything like that. So then r naught is going to be 5i plus j plus 3k, and again, it's written in those components because that's what we were given in here in this vector form. So let's just continue along that. And then it's going to be plus t, and now the parallel vector is going to be, just times it by I plus 4j minus 2k, like that. And this is a t, not a plus. And then combine these all together. So multiply this inside and then add them all the terms up. So we're going to have a 5 plus, this is going to be ti. So 5 plus, I'll just write this as 5 plus t. This is going to be t times I, and then bracket, this is the I standard basis vector. And then the next one's the j, that's going to be 1 plus 4t. And this is going to be j, like that. All right, and then this is going to be plus, the next one's going to be 3, and minus 2 times t. So 3, 2t, like this. And this is going to be k, like this. All right, so now we have this, wrote the k there, and so either of these will work because we're asked to find a vector equation and parametric equation. So this one is solved. So I'll just put this here as just for completeness. R vector is equal to this. So that's the vector equation. I just box it out, simplified. Either or, you could just highlight this one too as well, but just simplify to that. All right, so now that we have this vector equation, and now we can just get the parametric equations easily just by looking at each of these components. Because remember, if we scroll back up, if we have it in this form, so if we write the parametric equation like this, and then write it out in like this component form, then we can equate the components. X equals to this component, and Y and Z, etc. So parametric equation is pretty straightforward. So X is going to equal to 5 plus T. X equals to 5 plus T. Y equals to 1 plus 4T. And then here, next one's going to be Z equals to 3 minus T. Yeah, so those are the parametric equations, and that's pretty straightforward. And now as a double check, we could double check the graph using the GeoGebra 3D graphing calculator. So here you can write this in a vector form as R0513 like this. Here's the inputs I did. And then you could put the vector right here. This is for the parallel vector. You have to equate it. Or actually, I think I used this as a double check. I just forgot. So you could write vector here. This is 0.1513 to the 0.5. Then is added t is equal to 1 there. So yes, you go 5 plus 1. That's 5. Yeah, t is 1. 1 plus 4 times 1 is like this. And then it just correctly solves it as 1, 4, -2, exactly as this. Anyways, and there's the line right here. This is from the point here, 5, 1, 3, and then with the parallel vector v. And it writes it out like this. This parameter lambda is just t. This is just equals to t in the calculator. And it graphs it out like this. Pretty cool. You can even graph out the vectors as well. There's the vector in green here, 1, 4, negative 2, and there's the red 5, 1, 3, and it goes there. And it fits perfectly. Absolutely amazing. And if you click this, let's see what happens. So if I click this and it's opening up, yeah, so you can play around with it and see what you can find. This is a pretty epic calculator. And let's just see how it is. It's 3D graphing calculator. It's loading. Yeah, let's see how long it takes to load. All right. Yeah, pretty epic, guys. Yes, the amount you can see all the stuff. This is absolutely amazing. And you can play around with it. You could turn this vector off, on, this line off and on. Anyways, have fun with that. All right, let's continue further. So now let's take a look at the solution to 1b. So choosing the parameter value t gives, well, again, let's see what we're asked. We're asked find 2 other points on the line. So basically, we just add the parameter, change the value of t, and find points on it. All right, so let's say we have t equals to 1, and let's go back to our parametric equations. So 5 plus t, 1 plus 4t, 3 minus 2t. So we got 5 plus t, so x equals to 5. Yeah, this is a 5 plus t, and the other one's going to be, that's 5 plus t. So in other words, when we plug in t is equal to 1, that goes like that. It's equals to 6. Let's just double check again. Yeah, this is going to be 5 plus t, 1 plus 4t, then 3 minus 2t. So it's going to be y is equal to 1 plus 4 times by 1. That's going to be 5, like that. And then the last one, z is equal to 3 minus 2t. Yeah, let's say 3 minus 2t. 3 minus 2t. And then t is 1. This is equals to 3 minus 2 is going to be 1. Like that. Yes, so thus this point is just 6, 5, 1. So thus 6, 5, 1 is a point on the line. And similarly, choosing t equals -1 gives the point 4, -3, and 5. And we could see that here. So x equals to 5 minus 1. That's equals to 4. That's correct. And the next one, y is equal to 1 plus 4, -1. That's going to be 1 minus 4. That equals to -3. That's correct. The next one is z equals to 3 minus 2, -1. That's going to be minus plus, becomes a plus 2, so that's equals to 5. Like that. It's amazing. 4, -3, and 5. All right, continuing further, now let's look at direction numbers, and this involves a note on these examples that we just covered. So the vector equation and parametric equations of a line are not unique. If we change a point or the parameter, the parameter t, or choose a different parallel vector, then the equations change. For instance, if instead of 5, 1, 3 in this example there, we choose the point 6, 5, 1. In other words, choose this point here. This is also on the curve. In example 1, then the parametric equations of the line become, instead of this 5, 1, 3, it becomes this x equals to 6 plus t. Remember that other one's going to be the 5. Not the 5. It's going to be, this was y is equal to 1. Let's go back here. So 1, 1 plus 4t, and this one's 3 minus 2t, but then this is not going to be 1 anymore. It's going to be 5. It's going to be 5 now, because we're switching up this 1 with this 5. So it's going to be 5. Y equals 5, and this was going to be minus, not the minus, this is plus 4t. 4t, like, and then z is equal to, this is going to be now 1 instead of 3. 1 minus 2t. Yeah, so, or instead of switching up the starting position, or if we stay with the point 5, 1, 3, so we stay with this one, but choose the parallel vector 2i plus 8j minus 4k. And again, this is just a scalar multiple of this. We just multiply everything by 2 here. By 2, 2 times 2 is 4, 2 times 4 is 8. And then right here, negative 2 times 2 is negative 4. If we do all of that, we arrive at the equation. So x equals to, starting point is 5, plus, and instead of t, we're going to multiply by 2. It's going to be 2t. The next one's be y is going to be 5, 1. And this is going to be plus 4. Instead of 4, it's going to be 8j. 8t. We'll just switch up the parameters, the parametric equations. And lastly, z is going to be 1 minus 4t, like that. Actually, whoops, that's the 1 over there. That's this one. This is 3. So 3 minus 4t. So in other words, these all represent the exact same line because this is another parallel vector and there's another point on that line already. So yeah, we get the same line, just different equations for it, but same thing. Alright, so in general, if a vector v equals to components a, b, c is used to describe the direction of a line L, then the numbers a, b, and c are called direction numbers of L. Since any vector parallel to v could also be used, we see that any three numbers proportional to a, b, c could also be used as a set of direction numbers for L. Yeah, so you could switch them up to whatever they are as long as they're proportional, or in other words, scalar multiples of each other. And you can use this as the direction numbers, and then with any point, any starting point in this equation that's on the line. All right, now let's continue further. So symmetric equations of a line. So another way of describing a line is to eliminate the parameter t from the parametric equations. Yeah, so if none of a, b, or c is 0, we can solve each of these equations for t and equate the results and obtain. So what I mean by this is we can get rid of these parameters t like that. So yeah, so if we go back to our vector equation or just our parametric equations, we had before the example, we have x equals x naught plus at, and then y equals y naught plus ab. And this is actually a t, and bt. Get that mixed up. Yeah, so anyways, if we have this, let's go back here. And yeah, so if none of them are that, we could rearrange it. So if we have x is equal to x naught plus at, now we could solve this for t. So move this over to this side, and then divide it out. And then divide this out like that. I'll just put a division sign. So this one we subtract, this one we divide, so we get a t is equal to x minus x naught over a, like that. And then the next one is y is equal to y naught plus bt. And then likewise, we do the exact same thing. Move this over, and then divide this out. We get t equals to y minus y naught over b. And then last one, z is equal to z naught plus ct. And then rearrange this, move this over, just for completeness, put the arrows in there. T is equal to z minus z naught over c. All right, and then thus put these all together, we get t is equal to, and then equate all of these together. And they're symmetric because they're all the same. They're all equal to t. X minus x naught divided by a is equal to t. Well, these are all t. If y minus y naught over b equals to z minus z naught over c. And then we can box these in like that. Yeah, so these equations are called symmetric equations of the line L. So notice that the numbers a, b, and c that appear in the denominators of equation 3, or I'll just call it the equation above. Equation 3 that was labeled by the calculus book, but I just like writing this the equation above here, are direction numbers of L. Yeah, so note that these are the direction numbers. Remember the vector v, a, b, c. Those are direction numbers of L. That is components of a vector parallel to L. So if one of a, b, or c is 0, because then you can't divide by 0, we can still eliminate t. For instance, if a equals to 0, we could write the equation as follows. So instead of this, we can't do this. But if a equals to 0, we could just start off with x equals x naught, and then the other ones leave that in. So we could write, so if we have, for example, if a equals 0, we have x equals x naught plus a t. So this goes to 0, because a is 0. I'll just leave it like that. So then this equals to, this will just be x naught plus 0, like that. So in other words, we get x equals to x naught. Or else I'll do that after, just make it for completeness. This equals to x naught. So what we get is the equations x equals to x naught, and then we have the symmetric equations y minus y naught over b, because these ones are non-zero, and then z minus z naught over c. And there's our new symmetric equations. And now this means that L lies in the vertical plane x equals x naught. And here I'm actually going to draw this out just to illustrate this. So it lies on the x equals x naught vertical plane. So for example, if you had just xy graph like this is the y, this is the z, and I'm just going to draw a plane like this. And then this is going to go through it. This is the x naught, I mean this is x. And then this plane right here goes across like that. And let's say at this point right here, let's say this point crosses through it. This is at x naught. So this means that the line's going to be on this plane, and it's going to be something like this. That's going to be our L. Like that, or it could be like this, etc. It doesn't matter, but it's going to be on this plane, like that. And that's how you write this, yeah, x equals x naught. Yeah, so it doesn't matter what z or y value there are, you're always going to be on this x naught vertical plane. Alright, so let's continue further and look at example 2. And this one states, find parametric equations and symmetric equations of the line that passes through the points A, which has coordinates 2, 4, negative 3, and the point B, which has coordinates 3, negative 1, and 1. And then part B states, at what points does this line intersect the xy plane? Alright, so let's go over number A first, or question A, so solution to 2A. Let's first graph out the lines to better visualize this. So it's going to look something like this, and this is our Z, and this is our Y. It's going to look something like this. Our Y is going to be like this. And actually extended it past on the negative side, and let's say we have our X is going to be like this. Like that, that's our X. And so now let's graph out the point A. Yeah, so the point A goes to 2, 4, negative 3. So it goes 1, 2, and then it goes to 4. 1, 2, 3, 4. And it's going to go in on the negative side now. So I'll draw this like that. And it's going to go 1, 2, 3. So it's going to look somewhere like this. If we draw it across there, it's going to be like this. This is going to be our point A. Like that. And then the point B is going to be 3, negative 1, and 1. So it's going to go to 3 here. And then it's going to go to negative 1. So it's going to go back 1. And it's going to go up 1. It's going to be up like that. So it's going to be somewhere around here. Let's see if we draw it in 3D. It's going to be, this is our point B, like this. And then the line is going to be across like that. Alright, and this is going to be our line L. So just fix it up, write A right here. And A is, again, it's going to be at 2, 4, negative 3. Like that. And then the B is going to be, the coordinates are 3, negative 1, and 1. Like that. That's B. And then, and also in part A, it says at what points does this line intersect the XY plane? So it's going to be somewhere, it looks like somewhere around here-ish. Like that. That's, I believe, something like that. But anyways, I'll erase this, and then until we get it exact So now let's go further. Alright, so going further, so we're asked to find parametric equations and symmetric equations of this line pass through these 2 points. So we're not explicitly given a vector parallel to the line, but observe that the vector v with representation AB, so from here to B, is parallel to this line v, to this vector, or the direction vector. Actually, no, I mean parallel to the line, yeah. This is the vector, yeah. So it's parallel to this line right here. And we can write that out. That's just going to be v is going to equal to, well, the difference is going to be your position vector. V is just equal to, so it's going to be from A to B. So we're going to go 3 minus 2, like that, and then negative 1 minus 4, and then 1 minus 3. 1 minus negative 3. Like this. This is going to be 1 minus negative 3. Yeah, so this one minus this last one, and then just solving this is going to be 3 minus 2 is 1. Negative 1 minus 4 is negative 5. And then 1 minus negative 3 is going to be 1 plus 3. That's going to be 4. Like that. Alright, so thus the direction numbers are just the components of this parallel vector. So B, A is equal to 1, B is equal to negative 5, and C is equal to 4. And then taking the point A as a starting point right here, A is 2, 4, negative 3. As P naught, we see that the parametric equations are, and remember this one, the parametric equations are just going to be x equals to x naught plus AT, then y equals to y naught plus BT, and then we have z is equal to z naught plus, this is going to be CT. And then where these z naughts, etc., it's going to be this PO, and that's going to be choosing our point A. So this means that x is going to equal 2, it's going to be 2 is x naught, it's right here. Then plus A is 1t. So this is going to be plus t. Yeah, 1t, like that. And then y is going to be, this is y up. Yeah, so y is equal to y naught is going to be 4 plus, it's going to be negative 5 right here. So negative 5t. And then lastly, z is equal to, z naught is going to be negative 3. And then it's going to be plus c, which is 4t. Oh yeah, this is a 4 right there. And yeah, this is the negative 3 right here. Alright, and box this in. These are parametric equations of that line. Alright, so that's a parametric equation. Now the symmetric equations is just when we make t equals to each other. So we'll just make this, move this over, x minus x naught over a, then divide this out, etc. Do that for all of them. And essentially we just get that same setup here. So we get t is equal to, again, x minus x naught over a. And this equals to the same thing for the y. Do the same thing here. Y minus y naught over b. This equals to z minus z naught over c. And this will equal to, well, we know x, yeah, x is just general. X naught is just 2. So there's 2, then 4, then negative 3. And then this is divided by a, which is 1 here. Like that. This equals to y minus 4 over negative 5. This equals to z minus negative 3. That's going to be plus 3. Negatives become positive. Yeah, with 2 negatives. And then divide this by, this is c, 4. Like that. So there's our symmetric equations. Alright, so now let's take a look at the solution to B, and yeah, let's go over here. So again, yeah, we solved the parametric equations, symmetric equations, solution part A. Now part B says, at what points does this line intersect the xy plane? Alright, so that's a key factor. So the xy plane, like this means it's going to be this whole flat section actually. So that means to pass it is when z is equal to 0. Yeah, so it's going to be actually somewhere here. Yeah, so that's actually the point. It goes through the z equals to 0 setup across it. So what we could do is solve that. So the line intersects the xy plane when z is equal to 0. So we put z equals 0 in the symmetric equations and obtain. So we have these symmetric equations, put z equals 0 there. So we get x minus 2, yeah, divided by 1 and just ignores it. Divided by, yeah, equals to y minus 4, divided by 5 is equal to, well, z is 0. 0 plus 3 over 4. Well, again, this just equals to 3 over 4, like that. Yeah, so then we solve it for each one. So we'll have x minus 2 is equal to 3 over 4. And then move this 2 over to this side. We'll get, well, plus 2. And multiply top and bottom by 4. So we have the same common denominator. This equals 2. Actually, we'll do that after. So we move it over. And then we're going to have x equals 2. 3 over 4 plus 2. Again, times by 4 over 4. Like this. Write this a bit neater. The 2 here times by 4 over 4. Like that. I'll just move that up. So then 2 times 4 is 8 plus 3 is 11. So 11 over 4. So I have the same common denominator like that. And box this in. So that's our x value. And then the y value is, well, we equate the other side. Y minus 4 over negative 5 is equal to 3 over 4. It's equal to 3 over 4. Yeah, 3 over 4. Let's fix that up. And yes, move this around. So then multiply this by negative 5. Yeah, we move over this negative 5, multiply it out, and then move the 4 in. We'll get an equation for y. So in other words, we'll get y is equal to, we'll put the negative there, so negative 3 over 4 times by 5, and then minus, well, the minus becomes plus 4, like that. And then again, same common denominator, so times by 4 over 4. And 3 times 5 is 15, so we're going to get a negative 15 plus 16 over 4. That just becomes, this is negative 15, like that just becomes positive 1. 16 minus 15 is 1. So 1 over 4, like that. Alright. Yeah, so thus this means that, well, we have the equations, x is going to be equal to 11 over 4. That's just right here. And then we have y is equal to 1 over 4, where again z is 0, because it's crossing the xy plane. So then the point, we'll call this P, has coordinates, and this is going to be 11 over 4, 1 over 4, and 0, like that. Yeah, so thus the line intersects the xy plane at the point P, and then it has coordinates 11 over 4, 1 over 4, and 0. And we could draw that here. So then this is our point P. This is 11 over 4, 1 over 4, and 0, like that. Yeah, so 11 over 4 is going to be, well, 12 over 4 is 3, so it's going to be between 3 and 2. And then there's this 1 over 4, it goes pretty much like this, around there. It's going to be somewhere around here, actually. Let's just erase that. It's going to be somewhere around here. And move this over. And yeah. Alright, so that's the point. And let's continue further, and we can graph this out. So let's double check the graph using the GeoGebra 3D graphing calculator. So here you can make a line just from 2 points, 2, 4, negative 3, to 3, negative 1, 1. And it gives you the actual equation of the vector equation as well. And then I put the points on it, and there, and it shows the, and then I graph the point as well, 11 over 4, 1 over 4, and 0, and see where it lands. So there's the line. Yeah, it looks exactly like what we had. There's our A, there's our B, and then there is the P value right there on it. That's how the line looks like. Again, you can click the line, play around with it. So let's continue further and look at a note on example 2. So in general, the procedure of example 2 shows that that direction numbers of the line L, yeah, through the points P naught, which has coordinates x naught, y naught, z naught, and P1, x1, y1, z1, are, so the direction numbers are x minus x naught, y minus y naught, and z minus z naught. And so the symmetric equations of L are. And again, you can see that here because we were looking at the direction numbers, the A, B, and C. So this right here, A, B, and C. And we solve them by the difference of these 2 points. So this 3 minus 2, that's going to be, well, we can consider this as this is going to be, yeah, as x1 minus x naught, and then x2 minus, and then y2 minus, y1 minus y naught, and then z1 minus z naught. And those are the direction numbers there. So in other words, we could write this equation as, instead of A, we could write x1 minus x naught, etc. So we could write it like that because that is what it was. So 3 minus 2, that's just x1 minus x naught. All right. So let's write these out. Yeah, so we could write this all out. So we're going to have x minus x naught over, now the direction numbers are x1 minus x naught. Then likewise, it's going to be y minus y naught over y1 minus y naught. This equals to z minus z naught. Then z1 minus z naught. Like that. So epic stuff. Alright, now let's continue further and look at equation of a line segment as opposed to just a full infinite line. So often we need a description, not of an entire line, but just a line segment, but of just a line segment. How, for instance, could we describe the line segment AB in example 2? So how can we describe this right here from here to here, as opposed to drawing this entire line like that? So we just want the line from A to B, like that, so that line segment. Alright, so going further, so if we put t equals 0 in the parametric equations of example 2a, so those are right here, this parametric equation. If we put 0 here, we're just going to get x, we're just going to get the x naught, and then y naught, z naught. And then the next one we could just put 1, and then we're going to get actually interesting results. So let's take a look right here. So if we put it in, we get the point, well, 2, 4, negative 3, that's just a point A, and you could see that. Again, this is just x equals 2, and then let's just put that line again, plus, I believe this was 2 plus t, so going back here, this is, 2 plus t, then 4 minus 5t, and this is negative 3 plus 4t. Alright, and then y is equal to 4 minus 5t, and z is equal to negative 3 plus 4t. Like that. Then when you plug in 0, well, we get, so I'll just write this here for completeness. At t equals to 0, everything vanishes. We're just going to be left with x equals to 2, y is equal to 4, and then z is equal to negative 3. Which is, again, this point right here is just our a. A is a negative 2, 4, 3. Like that. And then if we put t equals 1, we get the point B, because this is just becomes 1, and that's just going to be the coordinates. You're subtracting the coordinates of actually, no, this is a direction number. So if we remember these equations, just teleport up here. These equations right here that we got, for example, this was AT, and then A was 1, where 1 was 3 minus 2. So in other words, in this first example, we have, this 3 minus 2, this is our x1. You can consider that as x1. So we have, we'll have it right over here. So x, let's write it here, x equals to 2. And then the 2 right here is just our x naught. This equals x naught plus, and then the a value, which was going to be x1 minus x naught, t. So then if this is equal to, and now that we have this written, I'm going to copy and paste this, and then let's put it down here. We get here, and if we look at it, if we plug in t equals to 1, we're going to get x at t equals to 1 is equal to x naught, then it's going to be plus x1 minus x naught, and then these just cancel. So the left with x1. So in other words, then do that same thing for y and z, we get the point B. So in other words, here at t equals to 1 for our scenario, we get t equals to 1, plug in 1 here. So 2 plus 1, 4 minus 5. So write this here. So this is going to be, this is going to be 3, negative 1, and 1. So you go plug it in 2 plus 1. 2 plus 1 is equal to 3. So that's correct. Then the next one is y is equal to, I'll just box this in. This is the correct answer. And the next one is going to be right here, 4 minus 5 times 1 is 1. 5 times t is 5 times t is just 1. It's negative 5. This equals negative 1. And that is correct. Yeah, and lastly, the z is going to be equal to, z equals to negative 3 plus 4t. So negative 3 plus 4, that just equals to 1. So 4 minus 3 is 1. Yeah, so the line segment AB is described by the parametric equation, because again, it ends up at B here. At t equals to 1, it ends up at B. At a t equals 0, it ends up at A. So now, in other words, all we need to do is solve it from t equals 0 to t equals 1. So in other words, the equation, I'll write this here, R of t, the line segment, this equals 2, and this is a vector equation form. And that is just putting these all together. So this is the parametric equation. So 2 plus t is the x component. And then we have y is equal to 4 minus 5t. And then we have this negative 3 plus 4t. Negative 3 plus 4t. And this is for t is less than or equal to 1 and greater than or equal to 0. So this is the line segment from A to B. Exit this. Alright, so going further, let's generalize this. So in general, we know from the earlier vector equation through the tip of the vector r naught in the direction of a vector v is r equals to r naught plus t times v. That's just the vector equation of a line. So if the line also passes through the tip of r1 vector, then we can take v is equal to r1 minus r naught, this vector, and so its vector equation is, and before I write that, I'm going to actually draw it out just to illustrate this graph. This is going to be our z actually, like that. So that's our z, and make this a bit less steep. And then this is going to be our y, and this is going to be our x, like that. So let's say we had a line L like this. Let's make it like that. This is our line L, and it has this from the origin. Let's say we have our R naught vector. So from the tip here is on the line. And now, let's say we had right here is going to be our R. So let's say this is our R. And this is our R vector, this vector equation. And before we draw the t, v, let's say we had R1 is somewhere here. So this is another point on the line, this R1. And now I'm going to draw this in red. So let's say we had a vector. This is the vector v. This is going to be v like that. This vector goes to like that, and well, from this vector you'll see that r naught is equal to r. This is going to be r naught plus v. So in other words, to solve this v, we just move this over to the other side, and we subtract it. We get this equation right there. And this is just a triangle law like this: r naught plus v is equal to r1, like that. And again, this just means that v is equal to r1 minus r naught, like that. And here I just change it to black felt like that, just to make it easier to see. So anyways, so that's that part. And this is our r, whoops, this is going to be our r. Our r is this one right here. And then the tv is going to be just a scalar times this v, and that's going to be across here. It's going to be like that. Whoops, that's just going to be, it's going to be, actually, I should make this a bit neater. So put the r naught here. This is going to be t v naught, or actually not v naught, I mean just v. And I'll erase that again. I'm just going to put this in blue, or this is not blue. This should be blue here. And let's make this in blue. And that's going to be like this. Alright, let's draw this again. So this is going to be TV vector. And here I just made it black just because it's easier to see. Alright, so that's what we have. So going back to this, we're going to solve the vector equation. So using what we know, using this v equals to r1 minus r0, just like this setup that we did, yeah, for the line segment right here. Yeah, in which we found a difference between a and b in the components, and so on. So let's go back here. So this is going to be now r vector is equal to, well, r0. So r0 plus triangle law tv right there. tv vector. And this equals to, let's write it all over here. This is going to be r0 plus, and then t, then the vector v is just equal to this part right here. So that equals to, this is going to be t times r1 minus r0 vector. And now we can just simplify this out. So multiply this t inside and separate the like terms. And what we get is, I'll write this like this. This equals to r0. I mean r vector, not r0. This r0 equals to, this is going to be, well, we're going to factor out, well, let's do this all on completeness. Yeah, let's do it all on completeness. I'm going to erase this. We're going to write this all later. So this equals to that. This equals to here, r0 plus t r1 vector minus t r0. And now we could separate factor out the r0s, the like terms. That's going to be, and then you factor out, it's going to be 1. I'll put it over here. And that's going to be 1 minus t. Like that. And then plus t r1 vector. Like that. And I'm just going to box this in. Like that. And now this setup here, if you look at it, it's the same thing as we had before. So if we put in t equals to 0, this vanishes, this becomes 1, so all we're left with is r0. Likewise, if you put in t equals to 1, this whole thing vanishes. This whole thing vanishes, and this becomes 1, and you're left with r1. In other words, it's exactly what we had earlier, but in that scalar format I wrote here. So x equals to x0 plus x1 minus x0. Like that, t. And then when you plug in t equals to 1, the x0s vanish. It's separate. So it's exactly what we just had, but here I'm writing it in vector form. So the line segment from r0 to r1 is given by the parameter 0 is less than or equal to t, which is less than or equal to 1. So t is from 0 to 1. Thus, we can summarize as follows. And this summary is right here. So the line segment from r0 to r1 is given by, it should be bold, given by the vector equation r of t, so r is a function of t, equals to this right here, 1 minus t r0, and then plus t r1 like that, where t is less than or equal to 1, greater than or equal to 0, like that. Alright, and again, as I just alluded to, notice that if we plug in t equals 0 or t equals 1, we get, well, r of 0, this just equals to, this is going to be 1 times by r0. Yeah, let's put it all together. 1 minus 0, r0 plus 0 times r1, like that. This just becomes, well, this is going to be 1, that's going to be r0 vector, like that. In other words, that's where it's going to that a value, or the starting point on the vector on the line. So and then r1, so t equals 1, we get 1 minus 1, r0 plus 1 times by r1. Let's leave that 1 out, and this is going to be r1. This just equals to, this vanishes, and we're left with r1, like that. Box this, and this one is the vector to that second point on the line, the b coordinate. I mean the b point with the yeah. So that's the r1 vector to the b point on the line. All right, now let's continue further and look at example 3. And this one states, show that the lines L1 and L2 with parametric equations shown below are skew lines. That is, they do not intersect and are not parallel and therefore do not lie in the same plane. So here's line L1, This is x equals 1 plus t. Then we had y equals to negative 2 plus 3t. And z is equal to 4 minus t. And likewise, x equals to 2s, y equals 3 plus s, and z equals to negative 3 plus 4s. That's better. All right, so let's take a look at the solution. And the solution here, so the lines, first of all, they're not parallel, so that they don't intersect and are not parallel. So they're not parallel because the corresponding direction vectors 1, 3, negative 1. You can see the direction vectors here is 1, 3, negative 1, and 2, 1, 4. So 2, 1, 4 are not parallel. In other words, their components are not proportional or scalar multiples of each other. And I'll just illustrate this further. I'm just going to write down both equations. So if we have R1 of t, this equals to, just in a vector format, the starting point is going to be 1, negative 2, and 4. 1, negative 2, and 4, like that. And then the next one's going to be plus t, and then it's going to be 1, 3, negative 1, like that. And these are the direction numbers, and then likewise for the second one, R2, I'm going to call this of s. And that is because the parameter here is s instead of t. So the point here is, well, this 2s, that's the direction number, and the starting position number of the x component is 0. It doesn't show there, so it's 0. And then it's going to be, the next one is 3. Next one is negative 3. And then the next thing we're going to do is plus s, the parameter, and then it's going to be 2, 1, so 2, 1, and then 4. Like that. And then you can see here, so these aren't all proportional. For example, this is a times by 2. Now let's do this better. So this, like that, that's 2x. This right here is divided by 3, so it's not the same one. This right here is going to be divided by, times it by negative 4. So this is negative multiplied by negative 4. So yeah, so they're not all proportional. Otherwise, yeah, to be proportional, you need to be all do the same thing, either multiplied by 2 or divided by 2 or divided by 3, etc. Alright, so we show that they're not parallel. So the next thing we have to do is show that they do not intersect. In other words, they don't intersect at a point where they share the same value. So if L1 and L2 had a point of intersection, there will be values of t and s such that, well, they're going to be the same. So we'll have all the x, y, z coordinates to be the same. So if we write that out, that means that we must have a scenario such that x equals to 1 plus t equals to 2s. So the x ones have to be equal. 2s. And then the next one is y. So we'll have y is equal to negative 2 plus 3t. So negative 2 plus 3t equals 2. This equals to 3 right here plus t plus s. That's 3 plus s. The next one's 4 minus t. So z equals to, the z's going to be 4 minus t equals to negative 3 plus 4t. I mean 4s. Yeah, so 4 minus t and then negative 3 plus 4s, like that. Alright, so if it had a point of intersection, they should have these set up where they're equal. And to show this, well, and also, yeah, and we're going to show that they do not intersect, so then they shouldn't have these numbers that equal each other. And so to do that, let's just solve it and see what we get. So if we solve the first two equations, we get, so solve these ones for s and t. So we get this equation 1, this is equation 2, and then this is equation 3. Like that. And I'll put it like this. Yeah, here, let's move this over further away so it doesn't look like it's part of the equation. So we have that. So then we're going to get 1 plus t equals to 2s. The next one's going to be negative 2, so put these all in line. 3t equals to, well, s plus 3. So let's cancel out some terms. Let's cancel out the t's. So to do that, I'm going to do is, well, multiply this entire equation by 3. And then we're going to do subtract this entire equation here. I mean, it's not multiply. We'll just subtract it. And we'll get an equation where the t's are canceled. So we're going to get a 3. Yeah, so 3 times 1. And then it's going to be minus, this is going to be negative 2, so that's going to be plus 2. Like that. Put a bracket. Like that. The next one here is going to be 3t minus 3t. So those just cancel. And yeah, over here is going to equal 2. Well, 2s, 3 times 2s is 6s minus s. And then we're going to have a minus 3 right here. So put these all together. We're going to get this equals to 5. 3 plus 2 is 5. This one cancels. Equals to 6s minus s is going to be 5s, then minus 3. And then move this 3 over to the other side and divide this 5 out, or just move it over. So we're going to get a 5 plus 3 is 8. So we're going to get an s equals to 8. And then divide this out, s equals to 8 over 5. Like that. Alright, so we have s equals 5. We could plug this inside equation 1. So we get 1 plus t. Yeah, 1 plus t is equal to, yeah, it's equal to 2s right there. This equals to 2 times it by 8 over 5. And here I put this inside like that. So inside the s. And now the next step is we'll move this 1 over to the other side. So we're going to get a t is equal to 2 times 8 is 16. 16 over 5 minus 1. Multiplied by that 5 over 5. Like that. So that we have the same common denominator. So 16 minus 5 is just going to equal to 11. 11 over 5. Alright, so now if we take these two values, so we have t and we have s. If we plug these values into the third equation, we get, so if we look at here, so 4 minus t and negative 3 plus 4s. So we'll get 4 minus t, like this. Yeah, so 4 minus t equals to negative 3 plus 4s. So they have to be equal like that. So then if we plug in t, so we're going to get a 4 minus 11 over 5 equals to, we'll move this arrow further, and then equals to negative 3 plus 4, and then s is 8 over 5. Times by 8 over 5, like that. And now what we'll do is, yeah, it's just keep solving it, but just leaving it in place. So here's some common denominators. I'm going to multiply this by 5 over 5. And that's going to be 20 minus 11. Or actually, better yet, instead of doing that, let's just get rid of the 5 altogether. So I'm going to multiply the entire thing by 5. So we're not changing anything. We're just scaling up everything by 5, but then the equations relative to each other don't change. So this is going to be equals to 4 times 5 is 20. So 20 minus 11 equals 2. And then here we're going to get negative 3 times 5 is 15. Like that. And then this 5 cancels. 4 times 8 is just going to be, well, 32. Like that. So then this part right here is going to be 20 minus 11 is 9. And then this part right here is negative 15. So 32, or 30 minus 15 is 15, plus another 2, so that's 17. So in other words, this is not equal to 17. So the equation is wrong. Yeah, I mean, they don't intercept each other, so we can't. So they don't have the same values there. All right. Yeah, so therefore there are no values of t and s that satisfies the three equations. So L1 and L2 do not intersect. Thus L1 and L2 are skew lines, so they're not parallel and they do not intercept. So here is a graph of the lines using the GeoGebra 3D graphing calculator, and there's line 1, 1, negative 2, 4, That's the point, and there's the vector 1, 3, negative 1. And you can see that over here. So 1, negative 2, 4, 1, 3, negative 1. So again, 1, 2, negative 4. And then the next one is 0, 3, negative 3. And then 2, 1, 4 is the vector. 0, 3, negative 3, 2, 1, 4 is that vector, direction vector. And if you graph it out, it looks like this. So the black one is, this one is L1. And there's the red is L2. And there's skew lines. So it looks like it's intersection, but it's not. If you turn it, the GeoGebra, you'll see that they don't actually intercept and they're not parallel. See, it's going outwards like that. Yeah, so it's the angle's getting bigger and bigger. All right, now let's go to the next section, and that's on planes or equations of planes. And the previous section was on lines. Now we're looking at planes. So although a line in space is determined by point and a direction, a plane in space is more difficult to describe, and that brings us to the vector equation of a plane. So a single vector parallel to a plane is not enough to convey the, quote, direction of a plane, but a vector perpendicular to the plane does completely satisfy its direction. Yeah, for example, if you had a plane like this, and then if you had a parallel vector, well, it could have multiple of them, so it's not specifying a direction, but you only have, well, one perpendicular vector to it. Yeah, so this is specifying its direction. If you shift it over, it's still the same vector there. You're just shifting the position, it's the same thing. Whereas a parallel one, you're going to have different actual directions. These are actual different directions, but it's still parallel. Anyways, going further. So, thus, a plane in space is determined by a point P naught with the coordinates x naught, y naught, z naught in the plane and a vector n that is orthogonal to the plane. And this orthogonal or perpendicular vector n is called a normal vector. So let P of with coordinates x, y, z be an arbitrary point in the plane, and let r naught and r be the position vectors of P naught and P. Then the vector r minus r naught is represented by P naught to P as a vector as shown in the figure below. So let's graph this whole thing out. So what I'll do is first I'll draw the plane first. Draw a big one like this. Let's say we had a plane like that. Alright, make this a bit better. Alright, so we have that, and now let's draw the z-axis. It's going to go like this, and I'll make a dashed line, dash, dash, across. And then here, just to signify it's 3D. And then it's going to go dash, 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 and goes across it. Like this. So this is the y. There's our x. Coordinate, x-axis. So let's draw all these out. Let's draw first the orthogonal vector. I'm going to draw, actually let's do the point first. Let's go P right here. So let's say we have a point P, and that's coordinates x, y, z. So an arbitrary one like that. And now let's draw a point here. This one here, we will call this, this is going to be our PO. So let's call this PO, and then its coordinates are x naught, y naught, and z naught. Alright, so we have this. Let's fix this up. And now let's say we have a orthogonal vector n, and let's say, let's draw a big line like that. This is going to be our n vector, and it's going to be perpendicular or orthogonal. And let's say we have a vector here, from here to here. And this one right here is perpendicular to it and is sticking out of the page. Or yeah, towards the out of the page. So, and this right here, let's say we had the position vectors now, and this is the origin. And this is going to go from here and then dot, 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 all the way across to this. This one is going to be our r naught vector. And then this one here goes across here and then goes all the way across here, dot, dot, dot. This is going to be our r vector. Just a regular r vector. And then the difference between here and here is just a difference. So we'll have r naught, r minus r naught. Because again, you could use the triangle law. So you'll have r naught plus this equals this. So then move that around, you'll get the difference. So anyways, it's going to be r naught like that. And yes, it's going to be r minus r naught. All right, now that we have this, going further, so the normal vector n is orthogonal to every vector in the plane. So it doesn't matter where the vector is, where you choose your p value there. It could be here, etc. It's all going to be perpendicular. This n is going to be perpendicular to it. So in particular, n is orthogonal to this vector r minus r naught, and using the fact that the dot product 0 for perpendicular vectors we have, and here's a link to my earlier video. So we're going to have just, well, the dot product of the normal vector to any vector on the plane, such as r minus r naught. This is going to equal to 0 because it's perpendicular. And so that's our plane equation. And let's box this whole thing in. And now this above equation, this can be rewritten as, we'll multiply this n times r, and then minus n times r naught, and move that over to the other side. We'll just write it as n times, n dot, so it's a dot product, equals to, let's make it bigger. So this is going to be n dot r vector, and then this equals to, again, it's a dot product, not just a multiplication. This is going to be now, it's going to be, and then you shift it over to the other side, n dot r, r naught vector. So you could write the equation of a plane in vector form in both of these formats. And move this up. And yeah, so either equation above is called a vector equation of the plane. And let's go further and now look at the scalar equation of a plane. So to obtain a scalar equation for the plane, we write the normal vector n with its components a, b, c. And let's say r has components x, y, z. And the r naught vector's components x naught, y naught, z naught. Then the vector equation becomes, so let's write this out. So we have n vector dot, this is going to be r minus r naught equals 0, and then plug in everything into it. This is going to be, this is going to be, well, the n is a, b, c, so this is going to be a, b, and c dot, and this is going to be now, well, these are subtracting from each other. Yeah, so just subtract these vectors, so it's going to be x minus x naught, and then y minus y naught, and then z minus z naught, components with a triangle bracket, equals 0. And now when you do the dot product, this is just a summation where this multiplies by this, plus, and then this multiplied by this, and then this multiplied by this, plus. So you add them all together. So let's do that, and that's going to be equals to a x minus x naught, and yeah, so a times x minus x naught plus b times y minus y naught plus c, and then z minus z naught. Now this whole thing equals to 0, and there's our equation of a plane, or scalar equation of a plane where there's no vectors involved. Yes, so this above equation is again called the scalar equation of a plane through the point p naught, x naught, y naught, z naught with normal vector n equals to a, b, c components, or has a, b, c components. All right, going further, so example 4, so this one states, find an equation of the plane through the point 2, 4, negative 1 with normal vector 2, 3, 4. Then we're asked to find intercepts and sketch the plane. So let's go over here. So putting in, so this is the normal vectors n. So n is equals a, b, c equals to 2, 3, 4. And p naught that goes through this point. So p naught's x naught, y naught, z naught. That's going to be 2, 4, 1. So we plug that into the scalar equation of a plane. We obtain, so we just throw that in there. So we obtain, so a is 2. So 2 and then x minus x naught is going to be 2. Plus, and then it's going to be right here, 3. Yeah, that's 3 right here. Times it by y minus, and then y naught is 4. And then plus, this is going to be, the next one is going to be 4. And then this is going to be right here, z minus this negative 1, that's going to be plus 1. Equals to 0. All right, so we have this. Now we could just simplify this further, multiply this inside. So we're going to get 2x minus 2 times 2 times negative 2 is negative 4. And this is going to be plus, and then 3 times y, minus, and then 3 times 4 is 12. So there's a minus 12 plus the next one 4z plus 4 equals to 0. So let's do some simplifications. Well, there's a minus 4, there's a plus 4. These can cancel. And then what we're left is, well, there's a negative 12 right there. So we can just move that over to the other side and then put everything else neatly to it. It's going to be a 2x and plus 3y plus 4z equals to 12. So there's our equation of a plane. Yeah, that's our simplified equation of a plane, but technically we could have just stopped right here. So we could have stopped right here, box this out, or we could do or, and then put it right here. All right, and now going further, so the next step is, well, to find intercepts and sketch the plane. So we find the equation of a plane, and we're going to find intercepts. So to find the x-intercepts, we set the y and z equals to 0, and then we could find the point that crosses that x-intercept. So if we set the y z equals 0 in this equation, and we can obtain, we'll obtain x equals 6. In other words, just throw that in there. We'll just double check our work. 2x plus, well, this is all 0, plus 0 plus 0, this equals to 12. And again, move the 2 over or divide it out, so x equals to 6, like that. And then similarly, the y-intercept is 4 and the z-intercept is 3, and we can check this out. Yeah, no, we could double check this again using this and then do the same thing. So to get the y-intercept, we make everything else 0. So we're going to get a 0 plus 3y plus 0 equals to 12. Like that. And again, divide by 3. This is going to be y equals to 4. And then similarly for the z, we make everything else 0. So we're just going to get 0 plus 0 plus 4z equals to 12, and then divide by 4. 12 divided by 4 is going to be 3. So z equals to 3. All right, so now that we have the intercepts, and this enables us to sketch the portion of the plane that lies in the first octant. In other words, that's all the positive values. And so again, we're asked to sketch the plane there. So it's going to look something like this. So we have the intercepts. So if we draw this out, what I'm going to do is, this is the z. I'm going to move this down until a point where we get the z equals 3. That's going to be the point 0, 0, and then 3. And then downwards is going to be like this. And then going further, now if we draw the other coordinate, the next one is the y is 4. So that means it's going to go like this. It goes across all the way until the 4. And this is going to be right here, this point. This point is going to be 0 is the x, 4 is the y, and then 0 is the z. And this is going to be our y. And then so then run a line like this. This is just the first octant. All right, now the next one is 6, so it's going to be further out. Be like this, dash across, all the way across. Let's say it goes something like this. Let's say it's here. Okay. So that is going to be, this point's going to be 6, 0, 0. All right. And then this means that it's going to be a triangle like that. Triangles is basically the side that's on, there's a triangle that's in the first octant forms a triangle. But then afterwards, it's going to, this whole plane is going to go below this xy plane. All right, and then extend this out. This is going to be our x, like that. All right, yeah, so that is the graph, and we can go further, and let's graph this using the GeoGebra 3D graphing calculator. And here's the inputs I did. I just put in the plane 2x plus 3y plus z equals to 12, and there's the points 0, 0, 3, 0, 4, 0, and then 6, 0, 0. And then I put the line segments from point 1 to point 2, and then also the point 1 to point 3 segment and point 2 to point 3. Anyways, you get a graph like this. And so again, there's a plane extending way beyond that triangle. But then you can graph the intercepts, and then it forms exactly what we just graphed there. There's point P1003, there's 040, and there's a 600, and I made it to the side so we can see this plane across like that. So again, you could play around with this link there. All right, now let's go further and now look at a linear equation of a plane. So by collecting the terms in the scalar equation of the plane, we could rewrite the equation of a plane as follows, and it also will look something like this, how we simplified it here. So if we go back to this plane equation, so write this out, then we could simplify it and then collect all of the constant terms, so such as this a, x naught, b, and then this b naught when they multiplied with each other. Yeah, so separate all those, and what we're going to get is, well, so let's just start collecting the terms. Let's just write down the scalar equation first. So x minus x naught plus b times y minus y naught plus c. And then let's erase this. Plus c, and then this is going to be z minus z naught. This equals to 0. And yeah, multiply this all inside. So what we're going to do is, let's just multiply it all out. It's going to be ax minus ax naught, and then plus by by naught, and then erase this. All right, it's going to be plus c times z times c z naught. This equals to 0. So we're going to collect all the like terms, move all the positive stuff, all the variables y, z all together. So that's just going to be equals to ax plus by plus cz. And then the next one's going to be, now we're just going to combine all these. I'm going to take out the negative as well. Take out the negative, and we're going to have ax naught plus by naught plus cz naught. This equals 0. And then specify this this term right here, this whole thing, this negative including, call this d. So then that means we could write this as a linear equation. We'll call this a linear equation. But this equation of a plane is going to be ax plus by plus cz plus d equals to 0. There's our linear equation of a plane, and this is going to be where, again, d for completeness is going to be equals to negative ax naught plus by naught plus c z naught, like that. All right, so going further, so this equation, this is called, the above equation is called a linear equation in x, y, and z. So conversely, it could be shown that if a, b, and c are all not 0, then the linear equation represents a plane with normal vector a, b, c, and it says, see exercise 1 at the end of the video. And basically it's saying, prove that this is an equation of a plane starting from here, or something, And it's pretty straightforward. You can just go backwards, and you can go backwards, but without needing to input this whole setup here, just with this d value here, and I'll show that in exercise 1 at the end of the video. Anyways, let's go further. So let's take a look at example 5. And this one states, find an equation of the plane that passes through the points P with coordinates 1, 3, 2, and Q with coordinates 3, negative 1, and 6, and R with coordinates 5, 2, 0. And then, so let's just go ahead and look at the solution right here. So we need an equation of the plane to pass through these 3 points. So the vectors a, b, let's call the vectors a and b corresponding to p, q. So we'll do the position vector from p to q, and then pr. So going from p, this one, and then this p to the r one and we just subtract the components of each one. So a is going to equal 2, so q terms, the q terms minus the p terms. This equals to, I'll just write this fully. So a equals to pq vector, or the position vector parallel to this one. And that's going to be, pq is going to be 3 minus 1. And then it's going to be negative 1 minus 3. Then it's going to be 6 minus 2. Like this. And this equals 2, negative 4, and then 4. Like that. And then box that in. And then continuing further, the next one's going to be B. This equals to PR. This equals to R is just 5 minus 1. And then it's going to be 2 minus 3. And then it's going to be 0 minus 2. And this equals to 4, negative 1, negative 2, like that. All right, so that's the two vectors, like that. All right, so now since both A and B vectors lie in the plane, because we're told that the equation passes through all these points, so the vectors that associated with them are all on the plane. So then that means their cross product, A cross B, and again, here's a link to my earlier video on it, is orthogonal or perpendicular to the plane and can be taken as the normal vector. Yes, the cross product gives a perpendicular vector of two vectors. So that means, and if we write this in determinate form, so we have normal vector n equals to A vector, A vector cross B vector. This equals to, write this in determinate form. It's going to be, let's write this out, the big table there. So I, 2, 4, the A is going to be right here, 2, negative 4, 4. Like that. And this is going to be J, be K. And then this next one's 4, negative 1, 2. So put the vectors in rows, in columns, like this. Yeah, so each row is a vector. So this vector, and then this one here. So negative 1, negative 2 right here. Whoops. Yeah, negative 2, like that. And then do this. All right, so if we take the cross product here, if we remember, what we'll do is cross out this to get the I terms, or this is in standard basis vector form. So we're going to have, well, this negative 4 times negative 2, that's going to be positive 8. Then we're going to subtract 4 times negative 1, that becomes, well, minus becomes plus, so it's plus 4. And this is the I, or the x component. And now the next step is, well, we'll cross this out. Erase that, cross this. So now what we have is, now we're going to have a minus. The middle one is a minus. And we're going to have 2 times negative 2. That's going to be negative 4. And then 4 times 4, so we're going to subtract 4 times 4, that's 16. Like that. And this is going to be J. Like that. And now the next one is plus. So plus, so that means we're going to, the next one is the K one, so we'll cancel out the K. So just remember this method. So now we go 2 times negative 1, that's negative 2. And then minus negative 4 times 4, well, it's a minus, becomes a plus, because there's another negative there. 4 times 4 is 16. And this is K vector. All right, so now what this equals to, let's just add it all up. So 8 plus 4 is 12. 12i, and then minus, this becomes, well, it's going to be plus. This negative 4 minus 16 is negative 20, then the negatives become plus 20j, like that. And the next one's going to be plus, negative 2 plus 16, that's going to be plus 14, 14k, like that. All right, so then this is the normal vector, and we can just box this whole thing out like that. All right, so now that we have the normal vector, and we also have the point P is 1, 3, 2. So yeah, we have a point right here. We could pick any point, I believe. Should all work out. But again, we did P, then PQ, PR, so we'll use the point P, so 1, 3, 2. So with the point P is 1, 3, 2, and the normal vector N above here, an equation of the plane is, and we'll just write down, remember it's going to be A, which is 12, and then X minus XO. X minus, well, XO is 1. And then we're going to have a plus, and then it's going to be 20. And then y minus yo, that's going to be 3. Then plus, this is going to be 14 is C. So that's 14 is C, and then it's going to be z minus zo, that's 2. Like that, this equals to 0. All right, so we could just stay with this. So that's our equation of the plane. Do a check mark, or we can continue further and simplify it further. And what I'll do is I'm going to divide by 2 on the whole thing, because you'll see there's a 12, there's a 20, there's a 14. So that's a factor of 2, and then we'll get a 7 there. So 7 should be, I can't divide that anymore by 2. So let's go ahead. This is going to be, so yeah, this is going to be 12 divided by 2 is 6. So 6 x minus 1 plus 10 y minus 3 plus 7 z minus 2 equals 0. And now we could multiply this inside, get a linear equation, and we could do, just go multiply it all out. So what we're going to get is, well, let's multiply all this, the variables. So 6x, 10y, 7z. So we'll get a 6x plus 10y plus 7z, like that. And the next one's going to be, well, 6 times negative 1. That's just going to be negative 6, like this. Yeah, negative 6, and then this is going to be 10 times negative 3. That's going to be negative 30. The next one's 7 times negative 2. That's going to be negative 14. And this equals to 0, like this. All right. And now let's just solve what this would be. Well, this is going to be, right here, this negative 6, negative 14 is negative 20. So then negative 30, negative 20, that becomes, well, negative 50. This whole thing's negative 50. Negative 50. All right, so it's negative 50, and now we'll just move it over to this side, so we'll get a plus 50 on the right side. So what we'll get is the linear equation 6x plus 10y plus 7z equals to 50. So there's a linear equation of a plane, more simplified than this equation of the plane, but this is still correct as well. All right, so now going further, let's graph this plane using the GeoGebra 3D graphing calculator. So you can plug that in. So 6x, 10y plus 7z equals 50. And then here's the points 1, 3, 2, 3, negative 1, 6, and then r is 5, 2, 0. And also, I did a double check actually. This was just for my own sake. So I did plane using their equation PQR, so 3 points. You just plug that in there, and it automatically solves the plane and the linear equation exactly what we had over here. Just quite remarkable. All right. And then I also did the segments from this Q to P, R to P, and R to Q, etc. And what we have is this. So there's a plane. I shifted it around so that we can see the plane and we can see the points on it. There's the P, Q, R right there, which is absolutely fascinating stuff there. And you can see it's right on the plane. And you can even see that with this, how this shaded area is at the bottom. So it's showing that it's on the plane there. All these are, you see the circle that's a half light blue, half dark blue. So it's literally crossing the plane, or just on the plane. So that's the circles cut in half there. Epic stuff. All right, let's make this actually a bit smaller maybe. Or just leave it like that. All right, it's pretty cool stuff. Anyways, now let's go further and look at example 6. And example 6 states, find the point at which the line with parametric equations x equals 2 plus 3t, y equals negative 4t, and z equals 5 plus t intersects the plane 4x plus 5y minus 2z equals 18. Alright, so let's take a look at the solution. So to find this point, so we want a point at which the line has these equations intersects this plane. So in other words, we could just throw these x values, for example, inside here, throw the y inside here, throw the z inside here, and then we're going to find a t value, and then we're going to just solve for the x, y, z. So we substitute the expression for x, y, and z from the parametric equations into the equation of the plane. So what we're going to get is, so we're going to get 4, so that's this 4x plus 5y minus 2z. This is going to be now 2 plus 3t, and then plus 5y, y is going to be negative 4t, and then the next one is is going to be negative 2z, negative 2, and then z is 5 plus t, like that. And then this is going to be equals to 18. Now we're going to solve for the t value. Well, let's multiply this inside. So we're going to get it 4 times 2 is 8, plus 12t, 3 times 4. Then here's going to be minus 20t. The next one's going to be right here, negative 10, negative 2t equals to 18. So what we get there, and let's see what else we get, is Yeah, it's right here. So so we have this. Let's move this everything over to the other side and then combine all the like terms. So I'll move this over to this side and this over to there. Now we're going to add up these like terms. So we're going to get a 12 minus 20 minus 2t equals to 18 plus 10 and then minus 8. So in other words, we're going to get 18 minus 8 is going to be, yeah, it's going to be 10. So we're, for example, this one, we'll just look at this one actually. 10 minus 8 is 2. So then 18 plus 2 is, well, it's going to be, this whole thing's going to equal to 20. Yeah, so that's going to be 20 there. Yeah, so that's 20. And then over here, let's just see what we get here. So 12 minus 2 is 10. Or we could just do it over here. So 12 minus 20 is negative 8. And then minus 2 is going to be, this is going to be negative 10. So in other words, we get a negative 10t equals to 20. Solve for t, divide this out. So t is equal to 20 divided by 10, negative 10. That's going to be negative 2. Alright, so therefore the point of intersection occurs when the parameter value is t. T equals negative 2. So plugging this value into the parametric equations of a line, we get the point of intersection to be negative 4, 8, and 3. And we could solve that here. So x equals 2 plus 3t. So we get x equals 2 plus 3t equals to, well, 2 plus 3 negative 2. So this equals to 2 minus 6 equals to negative 4. So this is correct over there. So that's negative 4 there. So the next one is going to be y. Y is just equals negative 4t. So y equals to negative 4t, which equals to negative 4, negative 2, which equals to plus 8. Like this. So that's plus 8. That is correct. Alright, write this neater. Alright. So this is correct. That's an 8 right there. Now the next one is z. Yeah, z is equal to 5 plus t. So equals 5 plus t. This equals to 5 minus 2 equals to 3. Alright, and that's 3. So that's the points. Alright, and continuing further, yeah, we can graph this as always using the GeoGebra 3D graphing calculator. Yeah, I like it. It's pretty epic stuff. You can double check your work and get some more insight. So here's the plane 4x plus 5y minus 2z. That is this right here, 4x plus 5y minus 2z equals 18. And then what you can do is draw a line, and then here's the line with the initial point 2, 0, 5. And yeah, that's the starting one. You could see that from the parametric equations. There is the 2, and there's a 0s in there, and then there's the 5. Those are the starting ones. And then it has a parallel vector 3, negative 4, and 1. I mean, yeah, that's a parallel vector right here. 3, negative 4, and 1. And then it gets you this vector equation, and it draws it, and there's the plane there, and then you have the point 4, negative 4, 8, and 3. Negative 4, 8, and 3. And it shows it across here. So there's the line L, and it intersects this plane, and you can see right at this edge there of this plane there, P is equal to negative 4, 8, 3. So yes, epic stuff. Again, you can click the link and play around with this and see what else you can find. Anyways, let's continue further. Alright, let's take a look at parallel planes. So two planes are parallel if their normal vectors are parallel. That is, it's a normal vector like this, and it's then you have another one like this as well, pointing in the same direction. Then you have the same. Then you have parallel planes. So for instance, the planes x plus 2y minus 3z equals 4, and 2x plus 4y minus 6z equals 3 are parallel because their normal vectors right here is 1, 2, negative 3. So 1, 2, negative 3, and this n2 is this is going to be 2, 4, negative 6. Yeah, so because that's their normal vectors, and n2 equals to 2 and 1. You can see these are just multiples of it. So all you're doing, these are parallel because you're just scaling these up by 2. You're just multiplying this every component by 2, like that. So it's exactly parallel. So this one, in this case, you have one one vector that's pointing this way, and then the other one is the same but double. So this is going to be 2x. So again, it's parallel. So then you're going to have parallel planes. And this term right here, the 3 and 4, that just shows it. Yeah, that just shifts it in space, but it's going to be still parallel. All right, so if two planes are not parallel, then they intersect in a straight line, and the angles between the two planes is defined as the acute angle between their normal vectors. Yes, and as shown in the figure below. So yes, if you have any non-parallel planes, they're always going to intersect, because you're going to infinity. And yeah, just geometrically speaking, it will intersect. So let's draw two planes. So let's say you had a plane like this. Here, I'll make this a straight line. Like this. And then you had another one. I mean, this is the same plane. Alright. So there's one plane. Alright, so let's say that's one plane. Now there's another one like this. And there's that angle to it. And I'm going to draw this angle as theta. So this angle, and I'm going to go as dashed lines across dot, dot, dot. And this dot, 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 dot all the way across here. Like that. So there's the line there. Alright, so let's say that at the bottom here of this plane is going to, we'll call that plane 1. That's going to have a, like this. Let's put a dashed line, going dashed up. Like this, dash, 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 and then it goes through this point all the way across, all the way on top here. This is going to be your n1 vector, like that. So now, because yeah, this one here is this is angles is theta like that. The next one is going to be, and this is from the bottom plane. The next one we're going to have, let's say it's going to be on this plane, on the top plane, and that's going to be, well, yeah, this is going to be pointing out like this. Actually, instead of going all the way there, let's make it right next to it. Yeah, just made it right next to it. And I'm going to do is I'm going to draw a line like this. This is going to be perpendicular to the top plane. And now we have an angle here. This angle is going to be also theta. And you can see this is a theta. This is exactly the same because you're turning it both by the exact same. For example, if you had it, if you had both of these flat, the angle is going to be 0. Theta is equal to 0. And then the difference between these are also going to be 0. They're pointing the exact same direction, so then the theta equals 0 on the top. And then as you rotate either or, yeah, so if you had, let's say you had here, and you had it flat, so you initially had 0, theta equals 0, and then you shift it. You can shift by exactly the same amount. Theta, theta. So that's all you're doing is turning it. So yeah, so the angle is going to be the difference between these. And this is going to be our n2. Alright, so now let's continue further and take a look at an example on this. So example 7, so part A states find the angle between the planes x plus y plus z equals 1 and x minus 2y plus 3z equals 1. And then part B states find symmetric equations for the line of intersection L of these two planes. Now we get an interesting little nugget here. So solution to 7a. So the normal vectors of these planes are, and again, the normal vectors is going to be whatever variable is in front of these x, y, z variables. So the first one's going to be, well, x plus y plus z, that's just going to be 1, 1, 1. So n1 is equal to the components 1, 1, 1. And then n2 is going to be 1, negative 2, and 3. 1, negative 2, and 3. Like that. Alright, so that is what we have. Alright, so if theta is the angle between the planes, we can apply the equation for the geometric interpretation of the dot product and get the following equation. Because yeah, so then basically we need to know the angle between the planes is just the angle between these direction vectors. So let's take a look at this. And if we recall from my earlier video, the geometric interpretation of the dot product is basically we get a cosine theta, angle between the two vectors is going to be equal to the dot product of two vectors. Divide this by the absolute value or the distance of the lengths of each one, multiplied by each other. like that. Yes, epic stuff. So this equals 2. So the dot product, this is, the top part's going to be the dot product. This is going to be 1, 1, 1, the two vectors, dot, 1, -2, -3. And now this is going to be divided by the lengths. Well, the bottom one, this is going to be length is going to be 1 squared plus 1 squared plus 1 squared. And then multiplied by, this is going to be this one here. 1 squared plus, this is going to be -2 squared, as this is going to be 2 squared. And then plus 3 squared, like that. So let's see what this gets. This one we know is just going to be 3. This part right here, or the inside, I was going to look at the inside. So this part right here, that's just going to be 3. This part inside is going to be, well, 1 plus 4 plus 3 squared is 9. So this is going to be 14. So the inside is going to be 14 like that. So put these all together, we get this is going to be equal to, this equals 2, and then here's the dot product. So this one's going to be 1 times 1 plus, so we multiply and add the components. 1, -2, that's just going to be -2. Those erases plus, put a -2. And then next one's 1 times 3, so plus 3. Divide this by square root 3 times by square root 14. Alright, so then what this is becomes, well, 1 plus 3 is 4, the -2 is going to be 2. And then this one here is 3, we could put the square roots together. 3 times 14 is going to be, well, 14 times 2 is 28, and then times by another, add another 14, so it's going to be 38, 42. Let's do that in our head. That's going to be 42 like that. So what this means is, this means that cosine theta equals to 2 over square root 42. So then the angle theta, we could use the inverse of it. So inverse, inverse theta. The inverse of this 2, 42 like that. So the inverse of that. Yeah, so this inverse or arc cosine of this 2 divided by square root 42. If you plug this into the calculator, what we're going to get is, well, this equals to roughly 72 degrees. Just quite epic stuff here. I'm going to box this in. Alright, so that's 72 degrees. And now we could do a calculation check. So we could write a cosine, the same thing as arc cosine or inverse cosine like that. And then 2 divided by square root 42. And this is using my built-in OneNote calculator. So we go equals space, and it goes automatically calculates it. So 72.02, etc. So yes, it rounds up to 72 degrees. It rounds down to 72 degrees. Epic stuff. And now let's graph out the planes and double check our work using the GeoGebra 3D graphing calculator as always. So here's the first plane, P1, plane 1, x plus y plus z equals 1. Then P2, x minus 2y plus 3z equals 1. And then what we could do is also calculate the angle directly using GeoGebra. So angle of the planes P1, P2, 72.02. Absolutely remarkable stuff here. And here's the graph of it. So there's the plane, and there's the other plane like that. The green is the plane 2. So this is P2, P1, and there's the angle 72.02, all shown automatically in 3D. Epic stuff here. All right, now let's take a look at solution to B, and this is finding the L that intersects those two. So find symmetric equations for the line of intersection L of these two planes. So what we're asked to find is this line that's intersecting here, like that. That's intersecting these two planes across like that. Epic stuff there. All right, so we first need to find a point on L. For instance, we can find the point where the line intersects the xy plane by setting z equals to 0 in the equations of both planes. Yeah, so when we plug in z equals 0 into the equation of both planes, well, again, we're just kind of guessing that it would be crossing there, because the line theoretically could never cross that xy plane. And yeah, so this is the x, this is the x, this is the y. The red is the x, there's the y, and there's the z up top here. But looking at the graph here, it looks like, yeah, it should cross it somewhere across. Somewhere across there, it's going to cross the z equals 0 plane there, or the xy plane. But yeah, so you can, again, trial and error, but in this case, it actually does. So, for instance, we can find the point where the line intersects xy plane by setting z equals 0 in the equations of both planes. This gives the equations x plus y equals 1 and x minus 2y equals 1. So if you look at the two planes, so right here, yeah, you just get rid of this this z, this goes vanishes, so x minus 2y equals 1, and x plus y equals 1. And let's see if we get values for those. And then whose solution is z equals, x equals 1, and y equals 0. And again, you can see that, so we'll have this x plus y. X plus y equals to 1. And then the other one is going to be x minus 2y equals to 1. And again, just double check there. Yeah, so then there's x plus y, then the z goes 0, x minus 2y plus 3z. And the 3z goes 0. So what we have here, yeah, so we have this. We have these two equations. There's an x and x line up, so we just subtract this whole thing at the bottom. And then get a third equation. So that it cancels out. So x minus x is 0. Y minus negative 2y is going to be plus 3y. And then this 1 minus 1 is 0. So we get 3y equals to 0. This means that y is equal to 0. So 3 just divided out goes to 0. Alright, so y is equal to 0, so that's correct. And then the last one, we just plug that inside. So this means now we'll get x plus, that's this part right here, x plus 0 equals 1. So in other words, x equals 1. Yeah, so we have these 2 points, or these 2 values. So now we have the point. It's going to be 1, 0, 0. All right, yeah, so the point 1, 0, 0 lies on L, since this point satisfies the equations of both planes. Now we observe that since L lies in both planes, yeah, so then it is perpendicular to both of the normal vectors. Yeah, so this means that a vector v parallel to L is given by the cross product, since the cross product gives a perpendicular vector. So for example, if you have these 2 planes, so you had one plane like this, has a normal vector. Let's call that n. This is let's call it n1 or n2. Actually, if you look at that, that's the green one. That's n2, like this. So that's n2, and then the other one is over here. It's going to be n1. Perpendicular to this. So these are perpendicular, it's not perpendicular to this one. It's perpendicular to the plane, like that. And then this one is perpendicular to the green one, etc. So let's ignore those. I'll just erase that. So yeah, so we have those perpendicular. We'll make this a bit less looking like it's perpendicular to it. So this is like that. It's going to look something like, yeah, let's just call it like that. Alright, so then the cross product is going to be parallel to this line right here. This is going to be the cross product. Like that. So it's going to be parallel, it's going to be perpendicular to these two. Like that. But also it's going to be parallel to this line L, so that we know the direction of it. So basically we know the direction, and we have a point on that line L. That means we can write the expression for that, the full line. And yeah, so we could just do the cross product of that. So then the vector v parallel, the direction vector of the line L, is going to equal to the cross product n1 cross n2 vectors. And yeah, the cross product gives a perpendicular vector to these vectors that are perpendicular to their respective planes. This equals to, as always, I, j, k. And then the components, so then n1 vector is just going to be 1, 1, 1. 1, 1, 1. And the next one is going to be, let's just go all the way up here. Yeah, so that's 1, 1, 1. 1, negative 2, 3. So 1, negative 2, and 3. 1, negative 2, and 3. And now we'll do the cross product as always. This is going to be equal to, cross this out, 1 times 1 is 3. 1 times 3 is 3. And then minus 1 times negative 2 is negative 2, but we're minusing, becomes plus 2. like that. This is going to be I. And then subtract is the middle one. Erase this. Erase. Now erase that, cross the middle. Now we're going to have a 1 times 3. It's going to be 3 minus 1 times 1 is 1. J. And then next one's going to be plus the K setup. So erase this. Cross this one. 1 times negative 2 is negative 2. Minus 1 times 1. Like that. And then just solve this out or simplify it. So 3 plus 2 is 5. And then minus 3 minus 1 is 2. Like that. And then this one's going to be plus negative 2 minus 1. That's going to be negative 3. So minus 3. Okay. Like that. And that is what we got. So 5, negative 2, negative 3. And let's circle this. This is going to be our V vector. Alright, and so the symmetric equations of L can be written as, and again we're asked for symmetric equations of the line as opposed to just the vector equation. So here, find symmetric equations for the line of intersection L of these two planes. And again, remember the symmetric equation is just when you have the parameter set that all equal to each other. So x minus x naught over A equals to y minus y naught over B equals to z minus z naught over C, where the where the A, B, C correspond to this vector V like that. So that means, or I'll continue it further. So where A, B, C equals to V vector equals to this components 5, negative 2, and negative 3. And also, and the components, the point here, x0, y0, z0, this is just a point on L. If we remember where we solved it for both planes, this was just equals to 1, 0, 0 as per the setup here. As per here. So we solve it here, the points x is 1 and then y0 is z0. And so that one lies on the plane, on the point L. Yeah, so we'll put this all together. We get x minus x0 is 1 over A is 5. This equals to y minus 0 is 0 divided by B is negative 2. And then this equals 2 z minus 0 is 0. Z minus 0 is just z. And then divided by C is negative 3. So there's our symmetric equations. Like that. Alright, so then we have the symmetric equations. Let's just graph this out. So let's graph out the line of intersection using, again, the amazing GeoGebra 3D graphing calculator. So there's a link to it, and there's the, I'm just using the same actual link as above, so KTTT, etc. Let's see this. K, T, 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 Fn, and so on. It's the same equation, just added more terms, just to add the line of intersection. So we could solve this. So there's a plane 1, x plus y plus z equals 1. There's the plane 2, x minus 2y plus 3z equals 1. There's the angle 72 degrees. And now what I did was I did a line, just using the vector equation. So there's the point line L, and then the vector 5, negative 2, negative 3 from the vector equation. From the, the vector 1. Here from the cross product. And then what happens is, you'll see this is the plane 1, this is plane 1, plane 2, and there's the line right there exactly on the intersection, which is absolutely amazing. So yes, it's a great way to double check your work. Alright, now let's continue further and now look at note 1. So two linear equations can represent a line. So since a linear equation in x, y, and z represents a plane, so linear equation is a plane, and two non-parallel planes intersect a line, it follows that two linear equations can represent a line. So when you have two linear equations, then the intercept of that is gonna be, can represent a line if those planes are not parallel, which is epic stuff. So the points x, y, z that satisfies both a1x plus b1 y plus z1 z plus d equals 1 equals 0, and a2x plus b2 y plus z c to z plus d2 equals 0. These are linear equations. So the points x, y, z that satisfies both these linear equations, these points lie on both of these planes, and so the pair of linear equations represents the line of intersection of the planes if those planes are not parallel. For instance, in example 7, the line L was given as the line of intersection of the planes x plus y plus z equals 1 and x minus 2y plus 3z equals to 1. And now the symmetric equations that we found for L could be written as, and then we could go and write these out. First, what I'll do is I'll write down these symmetric equations from example 7. So x minus 1 divided by 5 equals y divided by negative 2, and then equals z divided by negative 3. So let's write this out first. X over 1 divided by 5 equals to y over negative 2 equals to z over negative 3. And let's just double check that again. So x minus 1 over 5, y over negative 2 is z over negative 3. So we have this. Now what we'll do is, we could take this and then write it separately. And then we could write this as x minus 1 over 5 equals to y, y divided by negative 2. So we could leave it like this. This is actually a linear equation. So I'll box this out. That's a linear equation. And now the next one we could do is take this and then write it out as y is divided by negative 2 equals to z over negative 3. So we get this, or just cancel all these negatives, just write y over 2, just make it simpler, equals to z over 3. Now this is a linear equation. Both of them are exactly the same as our other linear equations, just written a bit differently. And you can see that these are linear equations because we could just rearrange this, or not necessarily rearrange it, just look at this right here and then separate it out so that it looks like our typical linear equation form. So x over 5 minus 1 over 5. And then move this over to this other side. We're going to have a plus, so just shift this over to this side. We're going to have a plus y over 2 equals to 0. So then the ABC, let's just shift this over actually. What I'll do is I'll move this out of the way. Here, I just move this out of the way. Move it onto the other side. And then shift this over to this side. And let's see. Alright, let's do one more. And then move this over to this side. Yes, now we have that form. That's exactly how we had a linear equation. So x plus y plus z equals 1. But instead we have this 1 over 5x plus 1 over 2y. So then the a is going to be 1 over 5, b is going to be 1 over 2. And then the z1, the c is going to be 0. And then we're having is negative 5 there. So again, these are linear equations. Or you can move this over to the right side. It doesn't matter. Same thing. And then likewise, this one right here is going to be, this one's already done for us. Y over 2. Move this over to the other side. Z over 3 equals 0. So again, linear equations. All right. And these equations are, again, are a pair of linear equations. So they exhibit L as the line of intersection of the planes x minus 1 divided by 5 equals y divided by negative 2, and y over 2 equals to z over 3. So this part right here, either or. And then here is, as in the figure below, is from my calculus book. So there is the line of intersection L, and there's the two planes. So this top vertical one is this x minus 1 divided by 5 equals y minus, and y divided by negative 2. And then this slanted one is this y divided by 2 equals z over 3. And then we have an equation of a line right there. So the above figure shows that the line L in example 7 can also be regarded as the line of intersection of planes from its symmetric equations, which is quite epic stuff. So these are different planes from those other ones from example 7. So we can graph out the 4 equations of the planes, 2 from example 7 and 2 from the symmetric equations, and show that they all intersected at the same common plane, which is hashtag amazing. So again, from GeoGebra, it's the same link there. I just added more terms. So there's a plane 1 from plane 2 of example 7. And now here's a plane from symmetric equation 1. So x minus 1 divided by 5 equals y divided by negative 2. And there's the symmetric equation 2, y over 2 equals z over 3. So you could write it either or. You could write it as this, or you could write it as this, this format, and it'll just solve everything. And there's the angle, 72 degrees. And I actually, I hit it, so that's why it's not selected. So I didn't select it just to get it out of the way. Anyways, and now we have the line. Remember, the line is the same one from example 7, the 0.100, and there's that cross product 5, -2, -3, that parallel vector. And now there's the 4 equations. So there's the red and purple are the symmetric equations. So these are, yeah, this red and purple are symmetric, and they're different from these blue and green ones. And notice how they're all exactly intersect at the same line L, which is absolutely remarkable. Yeah, that's L. Absolutely amazing. And now going further. Alright, so yeah, in general, when we write the equations of a line in symmetric form, such as this one right here, x minus x naught over a equals to y minus y naught over b. And again, I like writing t equals just so that we always remember it's the parameter, or set it all equals on for all of them. And then you have z equals z naught over c. Yeah, so if we have these symmetric equations, this equation of a line in symmetric form, then we could regard the line as the line of intersection of the 2 planes. And again, you just separate these across. And you should also get another plane, this one here, and this equation, equate those. Yeah, I believe that should also work as well. All right, yeah, so then anyways, going further, so it's going to be the intersection of the 2 planes. So we'll have x minus x naught over a equals y minus y naught over b, and then I'll just shift this over. All right, shifted it over, and we also have this one, y minus y naught over b equals to z minus z naught over c. All right, now here's another note, and I actually alluded to it earlier, is by using, well, this equation and this one, you know, those equating it as well. And that is right here. So note 2, line of intersection from 2 parametric planes. Again, this is a tied in note 1. So note that another way to find the line of intersection is to solve the equation of the planes for 2 of the variables in terms of the third, which can be taken as the parameter. So in our earlier example 7, we had x minus 1 over 5 equals to y over -2. This equals to z over -3. Yeah, so what we could do is, well, we take this and then equate it to this, and then also take this one and equate it to this one here. So what we'll get is, let's just write this out. We'll get x minus 1 over 5 equals to z over -3. And if we solve this, we'll multiply this 5 on top, and then shift this over. We're going to get x is going to equal to, well, 5, let's put the plus 1 in front. 1 plus, 1, it's going to be 1 minus, because there's a -3 there. 1 negative 5 over 3 z, like that. So that's one equation. And then the next one's going to be right here. And that's going to be what we already used to that one. Y over -2 equals z over -3. I'll write this better. Yeah, -3. And then multiply this inside. We're going to get y equals 2 plus 2 over 3 z. So the parameter is z right here. Parameter equals z, or parameter. Yeah, parameter equals to z. And yeah, basically the only difference is we have this equation now. Because this one here is the same thing as the other one we had that we graphed out. It's gonna be it's gonna be the same exact plane. That's this one right here. So y divided by -2 equals z divided by -3, or this equals to y over 2 equals z over 3. But now we have another equation, so all we're doing is adding another plane, and that's this one right here, because we equated this with the z. So that we get that plane. So now I have another one here, so I added parametric equations, I mean, from the symmetric equation, so S 1.2. So the second one, x equals 1 minus 5z over 3. Then we have S 2.2 is this right here, 2 over 3z. And these are the same exact colors because they're the exact same planes. All you're doing is shifting the 2 over to this side. All right, and now we have another plane. So we added all of them together. So now we have 1, 2, 3, 4, 5, 6. So we go 1, 2, 3, 4, and then there's 5. Yes, yeah, so 5 planes right here. 1, 2, 3, 4, 5, and then this one is the same as that. Yeah, so we have 5 planes all intersecting at this one line. Absolutely amazing. Which is yeah, quite fascinating. Yeah, fascinating little nugget there. Alright, and now let's continue further and look at example 8. And this one's on distance from a point to a plane. So we're asked find a formula for the distance d from a point P1 with coordinates x1, y1, z1 to the plane ax plus by plus zz plus d equals 0. So there's the linear equation of a plane. Yeah, so let's take a look at the solution. So let the p naught, x naught, y naught, z naught be any point in the given plane, and let b be the vector corresponding to the vector p naught to p1. So p naught to p1, that'll be the vector b, like that. Yeah, so in other words, what we get is, well, b vector is equal to, this is going to be, let's write this like this, p naught p1 like that. So the vector, this equals to, again, you just take a difference, so we'll go x1, so subtract the components, x1 minus y naught, y1 minus y naught, z1 minus z naught, like that. Alright, so now that we have this, so from the figure below, you can see that the distance d from P1 to the plane is equal to the absolute value of the scalar projection of b onto the normal vector n equals to ABC. So let's make sense of all this. And recall from my earlier video, scalar projection, I put a link to that one there. Yeah, so let's just make sense of all this and let's graph stuff out. So we'll have a plane like this. Alright, plane's gonna be like this. Alright, so the point P is a point P at P1 to the plane. So the point P naught is on the plane. So let's say we had a point P naught here. This one is on the plane. So this is P naught is on the plane. And let's say we had a point not on the plane or just any random point. This is gonna be our P1, like that. So that's P1. And then the vector b is from p naught to p1. So this vector right here, this is b vector like that. And now, so that's the plane. So now we have a normal vector here, n. And what we'll do is, from the figure below, we can see that the distance d is going to be, well, from, let's say you had a point right here across here. Or before we get to that, so let's say, look at this vector b. Now, if we project this onto the normal vector n, so the absolute value is going to be the distance. So in other words, if you project it all the way across to this point right here, let's say if we project it all the way across here to this, it's going to be a right angle. So when you have this, project this all the way on here, and then this angle is going to be, let's call this theta. And then this from here to here is going to be n. So there's the normal vector n. So then the distance right here is going to be from here to here is d. So that's the distance from there to there. And it's just a scalar projection of this b onto it over there. And first off, recall, and we're doing the absolute value. Recall right here, if you look at just basic trigonomic functions, if we take the absolute value of cosine here, cosine is going to be equal to adjacent over hypotenuse, and adjacent is d. Equals d over hypotenuse is the absolute value of this distance b, like that. Yeah, so then this is, so then a d is going to be equal to, shift this over, it's going to be like this. The distance, the length of the hypotenuse b times by the absolute value of cosine. We're doing absolute values just because we want the absolute values of all of these cosines and so on. Yeah, since we're dealing with absolute values, recall that this is from my earlier video just a scalar projection of b. So this is the scalar, and the way you write it is component of this is the component of b onto n, or the scalar projection. That's how you write it. But basically, it's just this part right there. And also recall that this angle right here of these two vectors, b and n, that's just a dot product. So we can also apply the dot product. Remember that cosine theta is equal to b, let's recall this, and cosine theta is equal to the dot product of b dot n, the two vectors with the angle between them, and then divided by the length b times by length n, like that. So then put this all together, what we end up getting is d equals to this right here, comp and the scalar projection. This is just the notation of how it's written. So this is the component of b onto n. I believe that's how it's pronounced. Alright, so we have this, and then we're taking absolute value, and then it's going to be the absolute value of that. It's going to be now, it's going to be this b right there, the length b, then there's cosine, we put that inside. That's what we put this inside here, so it goes down here. This is going to be b vector dot n, divide this by, there's a b on the bottom, like this, and there's the n. Alright, yeah, computer just froze for a bit. Anyway, so we have this, and this cancels, so we're left with, and this is, again, we're doing absolute value, so this whole thing is going to be absolute value. We'll put that in there. So we get b dot n dot, because we're doing absolute value of the distance, and then divided by the length n, like that. That's what we have. So anyways, this equals to, this equals to the dot product, the absolute value of the dot product is going to be, the b one right here is just x minus, it's just x1 minus x naught, etc. This is right all for completeness. So it's going to be x1 minus x naught, y1 minus y naught, z1 minus z naught, then dot, then the vector n is going to be abc. Yeah, this n is just going to be the abc, as per here. So normal vector is abc, like that. Alright, it's going to be a, b, c, and then absolute value divided by the n, the bottom is going to be the length. It's going to be a squared plus b squared plus c squared of the normal vector n. So then what we end up getting is, we'll multiply the a inside, keep going, so we're going to get a, put the triangle bracket in front, so we're going to get ax, actually we're not doing the triangle bracket because we're doing a dot product, so the dot product is a scalar, so then it's going to be a x1 minus x naught plus b y1 minus y naught plus c z1 minus z naught, like that, absolute value, and then divided by, and again it's frozen, so divide this by scalar a squared plus b squared and plus c squared, like that. So that's what we have, and then what's next is, well, we could simplify this even further, so multiply it out, just similar to how we made the linear equation for a plane. Alright, so this equals to, this is going to be ax1, multiply all these together and the other ones separately, plus by1 plus c z1, and then we're going to have minus, this is going to be minus, and then put a bracket, ax naught, and then the next one here is going to be minus, and there's a b, plus by naught, so we took the negatives out, plus c z naught, like that. And again, divide this by a squared plus b squared plus c squared, like that. Alright, so now that we have all this, so since P naught lies in the plane, its coordinate satisfies the equation of the plane, so we have ax naught plus by naught plus cz naught plus d equals to 0. Yeah, and we can see that above here. So we let P naught with coordinates x naught, y naught, z naught be any point on the given plane right here. So if you plug in these x naught, y naught, z naught, then yeah, that just equals to 0. The plus d equals to 0. So in other words, this part right here, let's move this like this, make some room. So then what we'll get is, if we write it like that, we'll get, if you make this whole thing over to the other side, we're going to get d equals to negative axo plus byo plus czo, like that. Alright, so we have this, so this is d. So this whole thing is going to be d now. Yeah, so this is d, right there. Yeah, so that's what we have. Alright, so thus the formula for d can be written as, well, we're going to have d equals to the absolute value of a x1 plus b y1 plus c z1 and then plus d, an absolute value, and divided by the length of the normal vector n, which is a squared plus b squared plus c squared. So let's box this whole thing in. Epic stuff. Alright, let's continue further and take a look at example 9. This utilizes this distance one. So we're asked to find a distance between the parallel planes 10x plus 2y minus 2z equals 5 and 5x plus y minus z equals 1. So let's take a look at the solution here. First we note that the planes are parallel because they're normal vectors. So here's a normal one here, 10, 2, negative 2. And 5, 1, negative 1 are parallel. That is, they are multiples of each other. They're just multiplied over here by 2. So 2 times 5 is 10, 2 times 1 is 2, 2 times negative 1 is negative 2. Alright, to find a distance between the planes, we choose any point on one plane and then calculate its distance to the other plane. So we just need to find one point. Yes, for example, if you have two planes like this, parallel planes, for example, we just need to find any point here and then apply the distance formula to this plane. So we just have point here and then plane here, for example. Alright, so in particular, if we put y equals z equals 0 in the equation of the first plane, we get 10x equals 5, and so 1/2 0, 0 is a point on this plane, and we could see this. So if we look at the first plane right here, 10x plus 2y minus 2z equals 5. So we'll go plug in z equals y equals 0. So 10x plus 2y is going to be plus 0 equals to 5, like that. So we get 10x equals 5. In other words, divide this out, x equals 2, 1/2, like that. And then we're going to get the point 1/2 and then 0 and 0. Alright? So, yes, so we could apply the distance formula. So thus by the distance formula, the distance between this point, 1/2, 0, 0 on the first plane, and then to the second plane, and the second plane, 5x plus y minus z equals 1, equals, this is minus z equals 1, not equals 0. Equals 0. No, actually, no, this was correct, because what we did, what the calculus book just did right here is it just took this negative 1, this 1, and moved it over. So to negative 1. In other words, so we have this format like that. So that's going to be d. D is equal to negative 1. Alright, so let's just plug this into the formula. So we get d equals to, let's write this whole thing out first, ax1 plus by1 plus cz1 plus d, absolute value, over a squared plus b squared plus c squared. And it's going to be on this plane, 5x plus 5 plus y minus z minus 1 equals 0. So that means the a is just going to be the terms in front of the variables. So it's going to be 5. And then x1 right here is going to be, well, the point, on the first plane. This is the second plane, so we're getting a point on the first plane. That's going to be this right here, 1/2, 0, 0. So it's going to be times it by 1/2. And then it's going to be plus 1 there, b is 1, times 0. Plus c is minus c. Then it's going to be minus c, which is 1 times by 0. And then plus d, which is negative 1. Minus 1, like that. Alright, so we have all this. And then that's absolute value. And then divide this by the length of the normal vector. 5 squared plus 1 squared. And there's a negative 1, that's going to be plus 1 squared, like that. Yeah, but for completeness, you could put a negative 1 squared, same thing. Negative 1 squared. So what we end up having is 5 over 2 plus 0 plus 0, minus 0, this is going to be minus 1, like that. And then there's absolute value sign, but then 5 over 2 is bigger than 1. We can just remove that absolute value sign. So it's going to be like this. Square root 5 is 25 plus 1 plus 1, 27. So square root 27. And erase this. Yeah, this equals 2. Let's multiply this top and bottom by 2. So then same common denominator. So 5 minus 2 is 3 over 2, like that. And then this part right here is interesting. So what I'll do is this 27, that's just the same thing as writing 3 times 9. And then we know that 9, square root of 9 is 3. So that means we could have a 3 over 2 over square root 3 times by 3. So then this cancels like that. And we're left with 1, this is going to be 1 over 2 square root 3. Like that. And here my calculus book actually simplifies this even further. It doesn't like having a square root at the bottom. I'll show this over here. So what it does is multiply the top and bottom by square root 3. So then basically what we'll get is this part of here will be, the square root 3's will become 3. Like that. So this will become square root 3 over 2 times 3, which equals to square root 3 over 6. Like that. Alright, and now going further, we can calculate this out. So the distance between the planes is square root 3 over 6, which equals to square root, you can just type this out in the calculator right here, SQRT, or square root 3 over 6. And using my, again, OneNote calculator, space equals to 0.2886, etc. It keeps going on and on. It's pretty amazing. I've built in OneNote calculator. Anyways, let's go further. So let's graph the two planes and calculate its distance using the amazing GeoGebra 3D graphing calculator. As always, it even has distances from planes. So here's the plane 1, 10x plus 2y minus 2z equals 5. And here's plane 2 in green, 5x plus y minus z equals 1. And calculate distance A, just type distance from between plane 1 and plane 2. It's just 0.29. Here's rounded up 288, rounds up 29. And there's two planes. There's the plane 1 is red, plane 2 is green. So notice they're parallel, and if you turn it around, you can see that they are indeed parallel, and the distance from here to here is 0.29. Absolutely amazing stuff. Alright, now let's continue further and look at example 10. So in example 3, we show that the following lines are skew. In other words, they don't intercept, and they're not parallel. So we have right here, line 1 is x equals 1 plus t, y equals negative 2 plus 3t, and then z equals 4 minus t. And line 2 is x equals 2s, and y equals 3 plus s, and z equals negative 3 plus 4s. So this is line 2, and there's line 1. So now we're asked, find a distance between them. Alright, so solution. Since the two planes, L1 and L2 are skew, they can be viewed as lying on two parallel planes, P1 and P2. For example, it just means that you'll have a line like this, so they're not parallel, but then so they never intersect, and they're not parallel. I mean, yeah, they never intercept. So imagine one line's on this plane, one line's on that plane. Then we could find a distance between them. All right, let's go further. So let's take a look at the solution. So since the two lines L1 and L2 are skewed, they can be viewed as lying on two parallel planes, P1 and P2. The distance between L1 and L2 is the same as the distance between P1 and P2, which can be computed as in example 9. So the exact same thing here. Just find a point, find equation of a plane, and solve it. So the common normal vector to both planes must be orthogonal to both V1, which is the direction angle of direction vector of L1. V1 is going to be in front of the t, so 1, 3, negative 1. So 1, 3, negative 1, this direction of L1. And V2, which is 2, 1, 4, direction of L2. So 2 is a 2s, 1, 4. So that's the direction of that line 2. Yeah, so the common normal vector must be orthogonal to both directions. So if it's on two planes like this and like this, so this is one direction, let's say V2, this one is V1, then the cross product is going to be a perpendicular, and like that, and it's going to be perpendicular to both, like that. So I'll just visualize this. And so a normal vector is orthogonal to both, and that is, again, that's the cross product. So n vector equals to V1 cross V2, which equals to our trusty I, J, K, like that. This is going to be the first vector is 1, 3, negative 1, 1, 3, negative 1. The next one is 2, 1, 4, like that. And now let's take the cross product as always. This equals 2, cross this out. We get 3 times 4 is 12, minus negative 1 times 1 is negative 1, so we have a plus 1. This is a negative there. Negatives becomes positive, and then the next one is, as always, so erase this one. All right, now we draw a line in the middle one, and then do the same thing there, but now we subtract. So 1 times 4 is 4, and then minus is negative already, so it becomes positive. 1 times 2 is 2. This is going to be our J, and then the next one is plus, and erase this. Next one is going to be erase the K, cancel out this. So 1 times 1 is 1, and then minus 3 times 2 is 6, like that. All right, so now the next step is, it's going to be 13 I minus 6J, then minus 5K, like that. All right, now I'm going to box this in, like that. All right, so now we have this normal vector n. The next thing that we could do is, well, if we put s equals 0 in the equations of L2, just to get a point on it, we get the point 0, 3, minus 3 on L2, and so an equation for P2 is, well, let's just write this down first. So if L2, so at s equals to 0, we get, well, if we take a look at the equations, yeah, so x is 2s, x is 0, so x equals to 0. The next one is y is equal to, just to double check here, the next one is 3 plus s, and the next one is negative 3 plus 4s. So 3 plus s, yeah, s is 0, just leave it like that. The next one is z is equal to negative 3 plus 4s, so that's going to be 0, yeah, so negative 3. So that is correct. Yeah, so we have this point is going to be 0, 3, negative 3. It's going to be on line, line 2. And so an equation for P2 is, so P2, let's write this down, P2 plane, this is the plane. It's going to be, well, we're going to write the normal vector. There's a normal vector 13, negative 6, 5, the components, and there's the point on this line, and we're going to say we're just going to form a parallel plane with this line on it. So that's going to be, or that point, yeah, so this point here on the line, and that's going to be 13, it's going to be x minus 0. And then minus 6, y minus 3, and then this is going to be minus 5, because this value there, that's c, minus 5, z minus the negative 3 is going to be plus 3. Like that, equals to 0. Alright, so this is the equation of a plane, but we could simplify it further. This equals to 13x, and then 0 is there, just eliminate it. Next one is going to be negative 6y, and then 5z, and then move this over inside. So negative 6 minus 3 times that is going to be plus 18. Alright, this is going to be plus 18. And then the next one is going to be negative 5 times 3, negative 15. This equals to 0, like that. So this becomes just 3. There's 13x minus 6y minus 5z plus 3 equals to 0. So this is our equation of the plane 2P2. Alright, here I just boxed that. And so now if we set t equals 0 in the equations for L1, we get this point here. So we have this plane right here for P2. So now we just need another point on P1, and then we could solve for using the distance formula from point to the plane. So if we set t equals 0 in the equations for L1, we get the point 1, negative 2, 4 on P1. And let's just double check. L2 at t equals to 0, we get, and if we scroll up, let's take a look here. So if we plug in 0, we'll get x equals 1. This goes to 0, so then y equals negative 2, and then z equals to 4. Yeah, so that is correct. So 1, negative 2, and 4. So x equals to 1, y equals to negative 2, and z equals to 4. Yeah, so thus the point is going to be 1, negative 2, 4 on, this is on L1, not L2. L1. Alright, so the distance between L1 and L2 is the same as the distance from this point right here on L1, 1, negative 2, 4, to the plane right here on parallel to L2. So it's 13x minus 6y minus 5z plus 3 equals 0. So thus, by the distance formula, the distance is d equals 2. This is going to be absolute value of a is 13. 13. Now we're going to multiply the x component of the point, so it's 1. And then it's going to be plus, but this is going to be minus right here is 6, negative 6. This is negative 6, and then it's going to be negative 2 is right here. And then this is going to be minus 5, and then this is 4 right there. And then plus d is 3. Like that, and then divide this all by the distance, or the length of the normal vector, so 13 squared plus negative 6 squared plus negative 5 squared. And let's just do some algebra fun here. So solve all of this. This is going to be 13 times 1 is just 13. Minus is going to be plus 12. 6 times 2 is, and then negatives become positive. And then minus 20 plus 3, like that. And then the bottom part here, well, what I'm going to do is I'm going to just put a side bubble right here. So I'll just multiply it on the side right here. So 13 times 13 to get the squared is going to be, well, 3 times 3 is 9. 3 times 1 is 3. Put a 0, just doing long multiplication. 1 times 3 is 3. 1 times 1 is 1. And now we're going to add these up. 9, 6, 1. Let's add. So this is equals to 169 plus 6 times 6 is 36. Negative 6 times negative 6 is also 36. Negative becomes positive. Negative 5 squared is just 5 squared equals plus 25. Like that. Alright, and let's do some more addition here. So 13 plus 12 is 25. Yeah, so just add a 10. 23 plus 2 is 25. And this right here is 17. Negative 17. So negative 20 plus 3 is negative 17. And the difference 25 minus 17, that's just, well, 3 goes to 20. And then 5, yeah. So 20 minus 5 25 minus 5 is 20, minus another 3, 17. So that's 5 plus 3 is 8. So that's going to be positive. It's 8. And now 169 plus 36, put it over here. It's 36. So 6 plus 9 is 15. Carry the 1. And then this is going to be 6 plus 1. 6 plus 3 is 9, plus the 1. So carry the 1. This is going to be 0. It's a 10. And then this is going to be 2. 205. And then add 25 plus 25. 5 plus 5 is 10. Carry the 1. This is going to be 3. This is going to be 2. This equals to 8 over square root 230. All right, and I'm going to put the d right here, and then this is going to be approximately equal to, when you solve it with a calculator, 0.53. So box this whole thing in. All right, and going further, let's do a calculation check right here. So we have right here 13 minus 6 times 12. That's this part right here. 6 times negative 2 minus 5 times 4 plus 3, and then use a calculator, press equals 8. That's exactly right. This next one is 13 squared. So 13 squared plus negative 6 squared, which is plus 6 squared plus 5 squared. And this equals 2, space 230. And then lastly, 8 divided by square root 30. Erase this, equals space, you'll see this. 0.527 round up to 0.53. So epic stuff there. So now let's graph and double check our calculations using, again, the amazing GeoGebra 3D graphing calculator. Here's the inputs I did. And here is the link right here. You can play around with it. And so there's the, I hid these vectors away. But anyways, going back here, I believe the skew lines were from example 3, I believe. But anyway, so here's the line. So what I have graphed here is line L1 right here with a 0.1, negative 2, 4. And then it has that parallel vector, or the direction vector V1 that we had, 1, 3, negative 1. Then there's other one was 2, 1, 4. And let's just scroll back to those direction vectors. There's V1 right here. V1 is 1, 3, negative 1. V2 is 2, 1, 4. And again, you could see that from the equations, from the parameters. So 1, 3, negative 1, 2, 1, 4. All right. Now that we have that, so that's the first line. There's a second line, and then the second line is 0, 3, negative 3, and there's 2, 1, 4, the direction vector there. Anyways, and then there's a cross product. I did a double check of the cross product V1, V2. So there's the V1, V2, and we get 13, negative 6, negative 5. So you can even do a cross product check as well. It's 13, negative 6, negative 5. It's absolutely amazing, all-in-one calculator right here. And there's the plane 1, 13x minus 6y minus 5z minus 5 equals 0. This one I actually had to solve it. I'll solve it soon. And then there's the other one that we had, P2, 13x minus 6y minus 5z plus 3. Because the calculator here only could do distances from between planes, not between point and plane for some reason. The distance P1, P2 equals 0.53, so you can actually solve the distance directly. And here it is when you graph it, you'll see the line 2 is parallel to this plane. This one's line 1 is parallel to that plane. And shift it around, looks like that. And there's the normal vector n. You can also draw the normal vector n right here with the cross product. You can even graph the cross product like that. And again, so that's what it is. And it's, again, it confirms our calculations. So note that in GeoGebra, the distance formula required that I know the equation of both planes, and in which I solved the first plane as follows. So the first plane, going back up here, so this is 13x minus 6y minus 5z minus 5. And to solve that, well, we need a point on the plane. So then that point is going to be 1, negative 2, 4. And we know, and then we just use a normal vector. So we can just solve that ourselves. All right, so let's go back here. So I solved it as follows. We had a point right here. This is going to be 1, negative 2, 4 is going to be on L1 and on the plane. So then P1 is going to be 13. This is going to be 13, negative 6, negative 5 is the normal vector. So P x minus 1, then minus 6 y, then minus negative 2, so be plus 2. and then minus 5 z minus 4 equals 0. Solve this out. This is going to be 13x. And then 6y over here, then minus 5z. Then move this over, so plus 13, negative 13. All right, this is going to be, negative 13, not plus 13. Negative 6 times 2 is negative 12. And then negative 5 times negative 4 is plus 20 equals 0. And let's do some addition. This is negative 13 minus negative 12. This is just negative 25. And then negative 25 plus 20, that's going to be negative 5. And there's our equation. 13x minus 6y minus 5z minus 5 equals to 0. And yeah, and you could confirm that it's correct because the distance formula, the distance gets it correct. So we're going back up here, scroll up. So there's that 13x, negative 6y, negative 5z, negative 5. And then we plug it into the calculator. P1, P2 gets 0.53 exactly as we calculated with the point to distance, point to plane distance formula. Whereas this one just uses plane to plane, but it probably uses variation of the same formula. Alright, and now finally, let's take a look at exercise 1, and this last example of this video. So if A, B, and C are not all 0, show that the equation ax plus by plus cz plus d equals 0 represents a plane, and A, B, C is a normal vector to the plane. So we're just given this equation, and we're given this d value to show that it's actually a plane. So hint, suppose A is not equal to 0 and rewrite the equation in the form A times x plus d over A plus B of times y minus 0 and then plus z times z minus 0 equals 0. So solution. So since A, B, and C are not all 0, then we can assume that then one of them is not 0. So let's assume A, one is not 0. If it's not A, we could do B, C, or whatever. Doesn't matter. So let's just pick A, and the result will mean that at least one of them is true. So hence the equation would be right if it is all true. So anyways, so what we have is, let's say we have, assume A is not equal to 0. So AX plus BY plus C Z, so we have this, and then plus D, like this. And then what I'm going to do is I'll multiply the top and bottom by A. And this equals 0. So now we multiply the top and bottom, we're not changing anything. And now we'll factor out the A out of there so that we get A x plus D over A. And then do the exact same format over here, but with the 0. So y minus 0 doesn't change anything. Plus c z minus 0 equals 0. Alright, and now we can rewrite this as a dot product. So we'll just, this is the same thing as writing it as, right here, A, B, C dot, and then this is going to be x plus d over A, and then y minus 0, z minus 0 equals 0. Yeah, because when you take dot product, you just multiply A inside this, and B inside this, and then C inside this one here. And we get this top part right here, which can be rewritten back into this format right here. So this one right here. Alright, so now we have this. This one here is our normal vector, because if the dot product is 0, so this is going to be our normal vector n. Alright, so now we have that. We can continue further and then separate this addition right here, or subtraction. Remove those. So what we're going to get is n vector dot, and this one here is the same thing as writing like this, x, I'll put a bracket here, so x, y, z, so move this x, y, z out, and then this is going to be plus the point dA. Well, actually, instead of using plus, we'll use negative. So then if we're taking a negative, and then to get to plus there, we need to also have this negative here. Just so that's familiar with the equation of a line that we had. Negative d over A, and then 0, 0. So we're subtracting everything. like that, equals to 0, like that. Now this one here, remember this is just our general position vector at any point. It's going to be r. This one right here is going to be our r naught. So a point on the plane, on the line. All right, so that's what we get is, well, this is going to be our n dot. Then we can do r minus r naught like that equals 0. And then the other format is, so we could stop it here. Or we could multiply this inside n r. So n dot r minus n vector r dot like that equals to 0. So we could do this, and then move this over, put this or right here, or finally move this over. This is going to be n dot r equals to n dot r naught. Put this like that. And these are all just the vector equations of a plane. So thus we have shown that the given equation can be written as a vector equation of a plane with normal vector n equals ABC and r minus r naught representing a vector on the plane. So there's this r minus r naught there. So fascinating stuff. Anyways, that is all for today. Hopefully you learned and enjoyed another epic long math video. And again, as always, I'm going to upload sections of these in a playlist format, so you can watch short clips of each segment and so on. And it's easier also to link back to them as well. So I can just link back to a specific video as opposed to this giant long video. For example, this one here is a section that I took from the dot product and made a separate video on the equation for the geometric interpretation of the dot product, as opposed to the full multi-hour dot product video. And you have to sift through it. But even then, that video, I put the timestamps in it as well. Anyways, that is all for today. If you learned and enjoyed, and again, the notes to all of these, the link to all the notes will be in the description below in both PDF format and article format, and timestamps will be there, and a link to the sections playlist, as well as the main 3D geometry playlist video, or the geometry of space. Let's see, vectors in the geometry of space playlist, all in the description below. And also make sure, just shout out to make sure to follow my Telegram for real-time research that I post everything on there. Conspiracy stuff, science stuff, math stuff, a lot of stuff. Anyways, thanks for watching and stay tuned for another Math Easy solution.